So from the previous discussions, right, for example, from this example, right, we can see that as you superimpose more and more of these complex exponentials on top of each other, you can construct periodic signals that are more and more sophisticated, okay, taking on arbitrary shapes that we like, okay. And in fact, for any signal x of t, you can also find its Fourier series representation with coefficients taken as the inner product between x of t and its corresponding complex exponentials. Now, previously we claimed without proof that any periodic, almost all periodic signals of interest can be written in this form. Okay, so it's of interest to discuss how this convergence occurs, right? So basically, we want to sort of see how this summation, as the number of terms grows to infinity, is able to approximate an arbitrary periodic signal, closer and closer. Okay. So to observe this convergence, we start out by looking at this truncated Fourier series representation. Right? So instead of letting n go to infinity, suppose that we start out by just looking at the superposition of the terms from minus capital N to capital N. Okay? So when you're not summing over all terms, there must be an error between the actual signal x of t and this truncated representation. Okay? And we define the error, we define the energy of the error as the integral of this error squared over one interval. Okay? So we're interested in only one interval because this thing is periodic, right? So it's sufficient to just look at one single interval. Now, suppose that you want to use this truncated Fourier series representation to represent the signal x of t, right? In that case, you would need to find the set of coefficients ak such that this error is as small as possible, okay? Or in other words, you want to find the coefficients ak such that the energy of this error is as small as possible. Now, how do you find the coefficients ak that minimizes this error, okay, the energy of the error? A way to do this is just taking the derivative of this with respect to the coefficient ak and setting it to 0, okay? So because this square term, right, makes this function quadratic, therefore this En, right, this energy, right, if you view it as a function of ak, is minimized when the derivative is 0, okay? So by taking the derivative of this with respect to the coefficient you're looking for, you can find the optimal coefficient, and it just so happens that the optimal coefficient is exactly equal to this formula that we derived before, okay? So what this is saying is that even if you just take a finite number of terms, the coefficient that we just derived actually gives you the best approximation of the original function x of t, okay? So if you want to look into further details of this optimization, you can look into problem 3.66, okay? Right. Now, this tells you that when you take a finite number of terms, the optimal set of coefficients, AK, is given by this formula here, okay? But what we further want to know is whether or not or when does the limit of this approximation, okay, truly approximate x of t as capital N goes to infinity, okay? So if we want to say, so if we want to say that this Fourier series representation truly exists for some periodic signal x of t, this means that we hope the limit of the truncated Fourier series representation approaches x of t as capital N goes to infinity. Okay? Okay. So when we ask, like, when does a periodic signal x of t have a Fourier series representation, we're basically asking when does x of n of t converge to x of t as n goes to infinity. Okay. Now there are different ways to look at this functional convergence. Okay, so there are different ways to look at this. So we won't go into details of these various types of convergence. Okay, if you want to know more about these different types of convergence, you can take a class on mathematical analysis. Okay, but for us, it's just good to know that there are various definitions of these convergence. Okay, and different convergence leads to different definitions of convergence leads to different conditions, right? Now, one notion of convergence is to have this En go to 0 as capital N goes to infinity, okay? And En is basically the integral of the squared difference between x of t and xn of t. Okay? So one convergence is to have this go to 0 as capital N goes to infinity. Okay? And this is the so-called L2 convergence. Right? And you can show that L2 convergence holds, okay, for any periodic signal with finite energy over a single period, okay, namely a signal that has an integral, right, where the integral of the absolute square of the signal, is finite over one period. Okay. Now, one thing to note is that even if, right, so if you have a little bit more knowledge about these various types of convergence, right, you should know that, this L2 convergence, right, having the energy of the error go to 0 does not imply that x of n of t is equal to x of t for all t, okay? So this is just one form of convergence, not implying, right? So this does not imply that x of n of t goes to x of t for all t. Okay? So this is a very strict form of convergence, right? This requires the convergence to hold everywhere, right, for all values of t, okay? But for many engineering applications, we do not need such a strict form of convergence, and often this L2 form of convergence is sufficient, okay? So if you want this convergence, right, if you want this Fourier series representation to hold in terms of this L2 convergence, then it's sufficient to have periodic signals that have finite energy over one period, right? And this includes almost all examples that we will encounter in practice, okay? Now, another form of convergence is to have convergence at almost all t, right? At almost all values of t except for some isolated points, okay? In that case, we say we have convergence almost everywhere. So if you want convergence almost everywhere, then one set of conditions is the so-called Dirichlet conditions, which includes three conditions, right? One is for the signal to be absolutely integrable over one period, okay? So absolutely integrable means that the integral over the absolute of x of t is finite over one period, okay? So this is a little bit different from before, right? So from before here, we have the energy, which has a square inside, okay? All right, so condition one is for the signal to be absolutely integrable. Condition two is for it to have, bounded variation, okay? So it should not have, infinite variations within a period. And in that case, this is equivalent to saying that there are only a finite number of maxima and minima within a period. And the third condition is that, also within a period, there can only be a finite number of discontinuities, okay? And each discontinuity has to be finite. So we won't go into the details of why these conditions lead to this almost everywhere convergence, but it's actually not difficult to imagine, because first of all, if you have if the signal is absolutely integrable, then this implies that the coefficient ak, which is less or equal to 1 over t, the absolute of x of t times e to the minus j k omega naught t dt. Okay. So ak originally is the integral of x of t times this, right? So it should be less or equal, the absolute should be less or equal to having this absolute inside the integral. Okay? And this is equal to 1 over t, the absolute integral of x of t, which is finite. Okay. So if the signal is absolutely integrable, this means that all your coefficients are finite. And it's easier to guarantee convergence in this case. Right? If you have coefficients that can potentially be infinite, right, then it's very difficult to prove that the two functions will have vanishing error. Okay? Now here we have a counterexample. Okay, so this is a counterexample. Okay, so a counterexample is having x of t equal to 1 over t within one period. Okay, so in this case, this blows up really fast as t approaches 0. And if you take the integral over 1 over t, it's actually unbounded. Okay. All right. Now the second condition is for x of t to have bounded variations. Okay. And another counterexample for this is the sine 2 pi over t. So for this function here, you will see that you have this fast, when you do not have bounded variations over one period, this means that it's possible to have higher and higher frequencies as you approach this 0 point for this example. Okay? So in this case, convergence is difficult to obtain because this means that your coefficient ak would be non-vanishing even as k grows up to infinity, right? Because you will have these infinite frequency terms in this signal. Okay? Right. And the same goes for this third condition as well, right? Because for the third condition, you have these infinite number of discontinuities. Okay? So with one discontinuity or a finite number of discontinuities, we can try to aggregate sufficient number of terms to try to approximate a function with a single or finite number of discontinuities. But when we have infinite number of discontinuities, this means, again, that we can potentially have high frequency terms that do not, that are not bounded, okay? Because we have to have more and more of these high frequency terms in order to approximate each one of these discontinuities, okay? All right, but in any case, you can sort of see that all these three conditions do not occur, in most practical signals that we would be interested in. Okay, so no matter which convergence that you're interested in, right, the main message here is that almost all signals of interest would allow us to have a Fourier series representation. Okay? Okay. So here we have this famous example of the convergence towards a periodic square wave. Okay? So here we're trying to use a superposition of these complex exponentials to approximate this square wave here. Okay. Now, if you take only one, if you take n equal to 1, meaning that you're taking the three terms k equal to -1, 0, and 1, right? You would get a signal that looks like this. Okay. Now, as you increase n, right, you will get these signals that become closer and closer to the square wave, right? Even though we may see these ripples along the surface. Okay. But these ripples become smaller and smaller, okay, as the number of terms increase, right? Now, what's interesting about this is that, when you increase the number of terms in the summation, right, even though the ripples become smaller and smaller, but you continue to observe this overshoot at the edges, okay? And this overshoot, right, the amount of overshoot actually never decreases, right? It actually always remains about 9% above the level, okay? And this is what we call the Gibbs phenomenon, okay? So when you're trying to approximate a function that is discontinuous, right, using these continuous sine waves, right, you will observe these Gibbs-like phenomenon around the edges, okay? But this is not a problem because as the number of terms n goes to infinity, this overshoot will go closer and closer to the edge, right? Will become closer and closer to the edge. So eventually, right, closer and closer to the edge. So eventually, for all terms, except for those terms at the point of discontinuity, we will observe convergence. Okay? So this is why, right, in this statement under Dirichlet conditions, it says that x of t satisfies its Fourier is equal to its Fourier series representation, except at isolated points at its discontinuity. Okay, and this is sort of observed from this example here. Okay. Now we can go on to show a few properties of the Fourier series representation. Okay. So these properties include things like linearity, time shifting, time reversal, right, time scaling, multiplication, and so on. Okay? So eventually, you can get a bunch of these properties in this table here. Okay. Now, all these properties you can derive in a straightforward manner. Okay? So let me just do this for a couple of cases. You'll see how this is done, and then you can try to do this for the remaining ones. Okay? All right, so let's start out with linearity. All right. So, so now we know that for almost all periodic signals of interest, x of t will have a Fourier series representation, okay, with coefficients ak. And we often denote this with x of t, double-sided arrow, ak, with fs on top to represent Fourier series representation. Okay? So this means that x of t has Fourier series coefficients ak, and using Fourier series coefficients ak, you can construct the signal x of t. Okay? So this is a shorthand for the Fourier series representation. Okay. Now what linearity says is that suppose you have two periodic signals x of t and y of t, both periodic with period capital T, and that they have Fourier series coefficients ak and bk respectively. Then if you take a linear combination of x of t and y of t, then the Fourier series coefficient of this superimposed signal will be equal to the same linear combination of their corresponding Fourier series coefficients. Okay? Now, it's straightforward to show this, and we'll do that below, right? So first of all, what this expression says is actually two things, right? First of all, z of t, the superposition of x of t and y of t, should have a Fourier series representation. And secondly, this Fourier series representation is also a superposition of these corresponding ak and bk's. Okay. So for this to have a Fourier series representation, you should first show that the zt is also periodic. Okay. And indeed, because xt and yt are periodic with the same period, therefore when you add them together, zt must also be periodic with the same period. Okay. And you can easily show this, right? Suppose you take zt plus capital T. Right, this is equal to ax t plus capital T plus by t plus capital T. Okay. And because x and y are periodic, therefore this is equal to ax of t plus by of t, which is just z of t. Okay? So hence, we know that z of t is indeed periodic with period t, and therefore has a Fourier series representation. Okay. So in this case, we can write z of t as summation of ck e to the j k omega naught t. Okay, so we can write zt using its Fourier series representation with omega naught that is 2 pi over capital T, right? Because the period is capital T. And the coefficient ck is 1 over t zt e to the minus j k omega naught t dt. Right. So this is integrating over one period. Okay. Now I can substitute this inside. So I get a 1 over t integral x of t e to the minus j k omega naught t dt plus b 1 over t integral y of t e to the minus j k omega naught t dt. Okay? And this integral is the Fourier series coefficient for x of t, which is ak, and this integral is bk. So this is equal to ak plus b bk. Okay, and this shows this statement here. So the proof for all these other properties are exactly the same. Okay, so for all these other properties, you just directly compute the coefficient of the new transformed function you're looking at, right? And you plug this inside, you will then find the corresponding relationship that you want. Okay. So for example, here you would be substituting x of t minus t naught inside here. And for time reversal, you'll substitute x of minus t inside here. Okay, so all of these you can get through direct computation. So tomorrow I won't be able to come to class because I committed to attending an event a long time ago. But in order not to delay our progress, I have posted videos for this chapter. Okay, so when you go back for tomorrow's class, for this part we're up to 3.5. Okay, so for this part we're up to section 3.5. So for tomorrow's class, please look at the video. Please watch the video up to 3.7. Okay, up to section 3.7. And that will be what we will cover in the midterm next week. Okay? So please watch up to section 3.7. Okay? And this will also be the midterm. Okay. So next Wednesday, I'll try to go through these parts, at least the main points of these parts again. Okay, but please still watch the video first. All right? I won't go into details. I'll just talk about the main points. Okay?
So I actually had a minor surgery yesterday morning. So I'm not sure if I can get through the entire class today. I'll still try to do so. But if I, feel uncomfortable along the way, then we'll maybe have to end early and pick up again tomorrow. All right. So last time last time we were talking about the existence of the Fourier series representation for periodic continuous time signals. Okay, so namely, we want to know when or what types of periodic continuous time signal x of t can be represented as this summation of ak e to the j k omega naught t. When you're asking whether or not such an expression exists, right, you can see that this expression involves a summation over infinite number of terms. So when you're asking whether or not this expression exists, you're essentially asking whether or not the convergence of this summation, right, as the number of terms that you add up go to infinity, will eventually converge to this function x of t. Now, you could be looking at convergence for all possible values of t, right? So you could be looking at this everywhere convergence, where the right-hand side converges to the left-hand side for all possible values of t. Okay, but this convergence is very challenging to achieve. Okay, and probably is not necessary in many engineering applications. Okay, so instead of looking at convergence everywhere, we looked at two other alternative notions of convergence. So one notion of convergence is convergence in the sense that the energy in the error vanishes as this capital N goes to infinity. Okay, so if you're looking at this notion of convergence, then it can be shown that any periodic signal with finite energy over a single period satisfies this convergence, right? Meaning that any periodic signal with finite energy over a single period has a Fourier series representation under this notion of convergence, right? The convergence in the sense that the energy in the error vanishes as capital N goes to infinity. Okay. Now, alternatively, Dirichlet gave us another notion of convergence, saying that actually this Fourier series representation converges to x of t, except at isolated points at which it is discontinuous, right? If the signal satisfies the following three conditions. So condition one is that the signal should be absolutely integrable over one period. Secondly, this signal should have bounded variation, okay? Bounded variation over a finite interval. Some signal like this, where the frequency increases to infinity as it approaches zero, would have infinite maximum minima over a period, and therefore does not satisfy Dirichlet conditions. Okay. Now the third condition is that there should be only a finite number of discontinuities, right? So if a signal satisfies these three conditions, then Dirichlet showed that this Fourier series representation converges to x of t almost everywhere except at isolated points at which there is discontinuity. Okay. Now these discussions tell us that almost all signals of interest in practice does have a Fourier series representation, right? So this sort of justifies the usefulness of this type of representation. Okay. Right. Now, last time we also went through a little history of the development of this Fourier series representation. Now, the source of argument, as we discussed, is mainly in the convergence of signals with discontinuities, right? So if you recall, Lagrange argument that the Lagrange argument for rejecting this this theory is that he believes the pluck of a string, right, will cause discontinuities in the signal that you cannot represent using these sinusoids. Okay. So sort of to address this concern, Michelson tried to look at the convergence of this truncated Fourier series for different values of n, okay, for a particular periodic square wave, right? So starting from n equal to 1, right, we can see that when n is equal to 1, there is only one sinusoidal component, and this this x sub n of t naturally deviates from this square wave quite large. Okay, but as n increases, right, this approximation given by the truncated Fourier series becomes closer and closer to the shape of an actual square wave. Okay, but if you look at these signals that we get, you will see that there will be ripples. There will be ripples along this along this horizontal line, and that there is a overshoot on the edges, which maintains to be about 9%, okay, regardless of what the value of capital N is. Right. So you can see that as capital N increases, these ripples becomes smaller and smaller, and eventually will converge to the flat surface of the square. But this edge, right, this overshoot at the edge actually does not decrease as capital N increases. Okay, and this overshoot by 9%, this observation is called the Gibbs phenomenon. Okay. Now, even though this overshoot always exists, even as n goes to infinity, right, you can see that this overshoot is pushed closer and closer to the discontinuity point as n goes to infinity, right? So as n becomes, as n goes to infinity, right, even though the overshoot still exists, it will eventually exist only at the discontinuity point, right, which still satisfies the convergence, the notion of convergence described by Dirichlet, right? So Dirichlet says that this converges at almost all points except at points of discontinuity. Okay. Okay, so this is where we ended last time. Okay. Now, so through these discussions, we now know that almost all periodic signals that we may encounter in practice has a Fourier series representation. Okay. Now we can derive various common properties of Fourier series representation, okay, that can be useful for us to analyze or compute the Fourier series of more complicated signals. Okay. Now, first of all, let us start by giving a notation for a periodic signal and its corresponding Fourier series. Okay. So suppose that AK is the Fourier series coefficient, is the set of Fourier series coefficients for the signal x of t, then we denote this by x of t, ak with a double-headed arrow, and fs on top to denote Fourier series. Okay, so when you see this notation, right, this is saying that, ak is the Fourier series coefficient of x of t, right? So given x of t, you can extract out ak, right, using, the formula that we, derived previously. And given ak, you can reconstruct x of t through the Fourier series representation, right? So this is a so-called Fourier series pair, right? A pair of signals and its corresponding Fourier series coefficient. Okay. Now we can show several, common properties of these, Fourier series representation. Now, first of all, starting out with linearity. Okay. So suppose that we have two signals, x of t, y of t, that are both periodic with period capital T. Okay. So it is critical to have both of these signals have the same period, capital T. Okay, so that they can be represented by the same set of harmonically related complex exponentials. Okay. So using the same set of harmonically related complex exponentials, x of t, we assume that x of t has Fourier series ak, and y of t has Fourier series coefficient bk. Okay. Then you can show that the Fourier series, so you can show that for z of t, that is equal to a linear combination of x of t and y of t with coefficients a and b, the Fourier series coefficient of z of t will be equal to a linear combination of the Fourier series coefficients of x of t and y of t respectively with the same Fourier, with the same linear combining coefficients, capital A and capital B. Okay. Now notice that, first of all, in order to have a Fourier series representation, you must first show that z of t is also periodic with period capital T. Okay. Now this is quite straightforward to show. Right. So note that, if you take z of t plus capital T, right, which is ax of t plus capital T plus b of yt plus capital T, right? By the periodicity of x and y, you can write this as ax of t plus b y of t, and by definition, this is z of t. Okay, so hence, z of t is periodic with period t. Okay. So if z of t is periodic with the same period, capital T, then you can express it in terms of the linear combination of the same set of harmonically related complex exponentials. Okay, so in this case, we can obtain the Fourier series representation of z of t as summation ck e to the jk omega naught t, k from minus infinity to infinity for omega naught, that is 2 pi over t. Okay. And then this ck here, okay, which is the Fourier series coefficient of the signal z of t, which you can obtain by taking 1 over t integral z of t times e to the minus j k omega naught t dt. Okay. Now you can substitute z of t with this linear combination of x and y above, and this becomes a 1 over t x of t e to the minus j k omega naught t plus b 1 over t y of t e to the minus j k omega naught t dt. Okay, and you can see that this integral here gives you the Fourier series coefficient of x, which is ak, and this second integral here gives you the Fourier series coefficient of y, which is bk. So therefore, this gives you ak plus bk, which is what we wanted to show here. Okay. So I wanted to, point out, one thing that people often neglect. So one important thing is that here x of t and y of t must both be periodic with the same period, capital T. Okay. So, the reason that this is necessary is because if you want to sort of perform computation on the Fourier series coefficient of these corresponding signals, then these coefficients should correspond to the same set of harmonically related complex exponentials. So if the two signals have different periods, then you would be using different set of if they have different periods, then their original Fourier series coefficient may be corresponding to different set of harmonically related complex exponentials. Okay, so in that case, you may have to find the common period of x and y in order to find the corresponding Fourier series coefficients for that common period. Okay. So this is actually, often assumed unless mentioned otherwise, right? So this is often not mentioned explicitly, but you should always be aware that this is a underlying condition that must be satisfied. Okay. Now, another common property that we often encounter is time shifting. Okay. So suppose that x of t has Fourier series coefficient ak, then a time-shifted version of x of t, shifted by t naught, has Fourier series coefficient bk that is equal to ak times e to the minus jk omega naught t naught. Okay. Or if you substitute omega naught with 2 pi over capital T, then this is what you get. Right. So to show this, first of all, right, in order for x of t minus t naught to have a Fourier series representation, this must also be periodic, okay, with period t. Okay. And this is also easy to show, right? So in fact, you can show that if you have x of t plus capital T minus t naught, right, by the periodicity of x of t, this is equal to x of t minus t naught. Okay, so hence, a time-shifted version of x of t is also periodic. Okay, and then to find the Fourier series coefficient by bk, we take 1 over t integral x of t minus t naught e to the minus j k omega naught t dt. Okay. Now we can perform a change of variable where we set tau equal to t minus t naught. Okay. So in this case, this becomes integral of x of tau e to the minus j k omega naught, where t becomes tau plus t naught. B tau. Okay. Right. So this t naught has nothing to do with tau, so I can bring this term outside of the integral, which gives me e to the minus j k omega naught t naught times 1 over t x of tau e to the minus j k omega naught tau d tau. And this integral here gives you the Fourier series coefficient for x of t. So this becomes ak e to the minus j k omega naught t naught. Okay. So you can see here that a time shift in the signal x of t gives you a Fourier series coefficient that has the same magnitude as x of t, but now with a phase shift of k omega naught t naught. Okay. So this shows that a time shift in x of t corresponds to phase shift in the Fourier series coefficient. Okay. Okay. So do we have any questions up to this point? 就到这边有没有什么问题？
目前没有问题。对。
OK。所以你可以了解说这个，就是说这样的一个 relationship 是怎么样求得的吗？就是说为什么 BK 会是 AK 乘上一个这个exponential 的这个phase shift？
可以，就是下面有推导出来嘛，就经过一个 tau 等于 t 减 t 0转换，然后就会求出来。
OK， 好，谢谢。所以我想这两个 example 其实大部分这些 example 都是蛮直接可以这个推导的就是从这个 Fourier series 就是我们前面给的这个怎么样 extract 这个 Fourier series coefficient 的 formula 就可以通过一个 straightforward 的 computation 得到。OK， 那我觉得大家可能稍微需要就是特别注意的，就是说就比如说在这个 time shifting 这边，其实我的 statement 里面并没有特别去强调x of t 或是 x of t 减 t naught 的这个 period，OK，但是当你提到这个 Fourier series representation 的时候，就是说你 implicitly assume 他们是会拥有同样的这个 period。Okay, well at least 就是说这个x of t has a period of capital T, and then for this relationship to hold, you would also need to show that x of t minus t naught also has this same period. Okay. So we can do one more example. So in this example, we're looking at the time reversal, right? Time reversal. So if x of t has Fourier series coefficient ak, then you can show that x of minus t has Fourier series coefficient a sub minus k. Okay, so time reversal in the signal corresponds to a time reversal in the Fourier series coefficient as well. Okay, so again, this is straightforward to show. Okay, so first of all, if x of t is periodic with period capital T, then so would its time reversal. Okay, so I'm going to neglect that discussion there. And to get the Fourier series coefficient of x of minus t, okay, so you could okay, to get this Fourier series coefficient for x of minus t, you could apply a formula similar to something above, but actually this could be observed quite easily by just writing out the Fourier series representation of x of minus t. Okay, so for x of minus t, the Fourier series representation is just summation of ak e to the j k omega naught minus t, right? So this is just the Fourier series representation of x of t with t substituted with minus t, which will give you x of minus t, right? Now, suppose you do a change of variable where you set m equal to minus k, then you again have a summation from minus infinity to infinity. But here you have a sub minus m, and up here, right, if you combine this minus sign with k, you get j m omega naught t. Okay, and this is the Fourier series representation for x of minus t. So this is saying that, so this shows that the Fourier series coefficient of x of t corresponding to the complex exponential e to the j k omega naught t is a sub minus k. Okay, so this is essentially what this notation expresses above. Now, consequently, okay, suppose that you have an even signal, right? So suppose that x of t is even. So if x of t is even, this implies that x of t is equal to x of minus t. Right. So if x of t is equal to x of minus t, then a sub minus k must be equal to ak. Okay, so then ak is equal to a sub minus k. Okay, which means that the Fourier series coefficient is even as well. Now, on the other hand, if x of t is odd, in other words, x of t is equal to minus x of minus t, okay, then this means that ak should be equal to minus a sub minus k, which means that the Fourier series coefficient is also odd. Now next, let us look at the concept of time scaling. Now, what is the Fourier series coefficient of a time-scaled version of x of t? Let's say x sub alpha t. So if you take this Fourier series representation, I think I have a typo here. Okay, sorry, I think I have a typo here. It should not be a negative sign. Right. So if you look at the Fourier series representation of x of t, but now just substitute alpha t into t, then you will get an expression like this. Okay. So if you observe this expression, then you will see that the Fourier series coefficients for this time-scaled version of x of t is the same as that of x of t. Okay. But you must be very careful here, because even though the Fourier series coefficients are the same, there are actually coefficients corresponding to different sets of harmonically related complex exponentials. Okay. So this is because, if x of t is periodic with period capital T, then this x of alpha t would actually be periodic with a scaled period. Okay. So this is actually periodic with period t over alpha instead of capital T. Or you can say that it has a fundamental frequency of alpha omega naught. Okay. So when you look at this, you can see that it has the same Fourier series coefficients, but for a different set of harmonically related complex exponentials. Okay. Right. Now, next, we can look at this property for multiplication. Okay, so suppose that you have two signals, x of t and y of t, that are both periodic with period capital T. Then first of all, you can show that the multiplication of both of these two signals are also periodic. Okay, they are also periodic with period t. Okay, and that the Fourier series coefficient of the product of the two signals is actually equal to the convolution of the Fourier series of their respective Fourier series coefficients. Okay, so multiplication of two signals in time will have a Fourier series coefficient that is equal to the convolution, the discrete time convolution of their corresponding Fourier series coefficients. Okay. Now you can also show this by directly, applying the formula for finding the coefficients, and I'm going to leave this for you to practice. Okay, so this is also done in problem 3.46 of the textbook. Okay. Now, the next property is conjugation and conjugate symmetry. Right. So this is saying that if x of t has Fourier series coefficient ak, then you can show that the complex conjugate of x of t has Fourier series coefficient that is equal to, a sub minus k with a complex conjugate. Okay. So this means that if you have a signal that is equal to a complex conjugate in the time domain, then the Fourier series coefficient will be so-called conjugate symmetric, right? It is symmetric after a conjugate, a complex conjugate. Okay. So you can also do this by direct observation of the Fourier series representation. So suppose you look at x complex conjugate of t. Right, so this is equal to the Fourier series representation of x of t complex conjugate. Okay. So when you bring this inside, you have summation k from from minus infinity to infinity ak complex conjugate e to the minus j k okay. And then by change of variable, where you set k prime equal to minus k, you get summation k prime from minus infinity to infinity a sub minus k prime complex conjugate e to the j k prime omega naught t. Okay, so this shows that the Fourier series coefficient of x of t complex conjugate is equal to a sub minus k complex conjugate. Okay. Now, if x of t is real, right, if x of t is real, which means that x of t is equal to x of t complex conjugate, okay, then this means that ak should be equal to a sub minus k complex conjugate. Okay, so this is saying that if x of t is real, then its Fourier series coefficient should be conjugate symmetric. Okay. Now, furthermore, okay, if you have x of t that is not only real, but also even, okay. Now, you know that if it is real, then ak will be equal to a sub minus k complex conjugate. Okay. So you know that if it is real, then ak will be equal to a sub minus k complex conjugate. And you know that if it is even, then the Fourier series coefficient should be even as well. Okay. So this is saying that if it is even, then ak should be equal to a sub minus k. Okay. So this implies that ak is also real because a minus k must be equal to its complex conjugate. Okay, and that it is even. So similarly, if you have x of t that is real and odd, okay, then you know that ak is equal to a sub minus k complex conjugate equal to minus a sub minus k. Okay. So if if the complex conjugate of ak is equal to minus itself, then this must mean that ak is pure imaginary. Okay, so this implies that ak is pure imaginary. Okay, and if it is odd, the Fourier series coefficient will be odd as well. Okay. So the last property I want to talk about here is Parseval's relation. Okay. So Parseval's relation is given by this equality here. Now on the left-hand side, right, what we have, on the left-hand side, what we have is 1 over t, the integral of x of t absolute squared dt over 1 period. So what you're looking at here can be viewed as the average power of the signal over 1 period. Okay. Now on the right-hand side, what you have is the summation of ak absolute squared. Now ak absolute squared right? Each one of these can be viewed as the average power in the kth harmonic component. Okay, in the kth harmonic component of the signal. Okay. Now this is because if you take the average power of the kth harmonic component, right? So if you take the average power, okay, of the kth harmonic component, which is ak e to the j k omega naught t squared dt, okay? This is simply equal to 1 over t integral ak squared dt. And the integral over a constant, right, over one period gives you the constant times capital T, which cancels out with this, and therefore this is just ak squared. Okay? So, you know, this relation here, right, this relation here, shape here is, can be proved by directly, you know, inserting the Fourier series representation of x of t inside this integral here. Okay, so this is also a straightforward computation, which is done in one of the problems as well. Okay, so let's leave this for problem 3.46. Okay, but it's actually very simple. You just directly substitute the Fourier series representation inside this integral on the left-hand side. Right. But this relation has has a very meaningful interpretation. Right. So it essentially tells you that the average power of the periodic signal is equal to the average power. The average power of all of its harmonic components. Okay, so this further validates the fact that this signal can be fully represented by a linear combination of these harmonic components. So again, do we have any questions up to this point?
老师，我请问一下，那个下面你那 IE 那边t 分之一 k ak， 然后 exponential 那一项，为什么平方之后它就变成1啦？就是可以算一下那个是怎么变成1的吗？
你说什么东西变成1？
就是底下蓝色的右下角那个 ak exponential 那边那一项。
哦 ，OK。
为什么会变成后面的
？OK。所以因为这个 ak e to the j k omega naught t absolute square， 所以 absolute square 就是这个数字乘上它自己的 complex conjugate，right？ 所以这个会是 ak e to the j k omega naught t times ak complex conjugate e to the minus j k omega naught t. So this times this becomes a constant 1, right? So what's left is ak times ak complex conjugate.
了解，谢谢老师。
OK。好，还有没有其他的问题？
教授。
还是？
我可以问一下上面那个 AK is pure imaginary 的是什么意思吗？
所以 pure imaginary 就是说它就只有 imaginary 那一项。
可是为什么？就是它是怎么导出来的？
因为我一个数字如果它的 complex conjugate 就是等于负的 本来这个数字的话，那这个数字一定是 pure imaginary。对，就是比如说你原本有一个讯号 a 加 jb 好了，那么你如果对它去 complex conjugate， 它是不是就会等于 a 减 jb？
对。
对。那如果说 a 是 non-zero 的话，那么这就不可能等于负的 a 加 jb， 对不对？所以如果 a 是 non-zero 的话，这个数字的 complex conjugate 就不可能等于负的原本这个数字。
哦，我懂了的，谢谢。
OK。好。所以那个谢谢世贤和子佑问这些问题。那我想这些问题应该是很多其他同学想问的啊。那不知道还有没有其他问题？ Okay. So even though all these properties are quite straightforward to show, right? I hope that through more and more practice, you will be able to know all of these properties by heart, right? Because these basic properties will give you, really good insight when dealing with signals that are much more complicated. Okay. So this in this table 3.1, we actually have a list of properties that are often encountered. Okay. So we did not go through all of these, but actually you can prove all of these following similar approaches. Right. So we only touched upon this linearity, time shifting, conjugation, time reversal, time scaling, multiplication, right? So if you recall, multiplication of two time domain signals has a Fourier series coefficient that is equal to the convolution of their corresponding Fourier series coefficients. Okay. Now, if you look at the property above, you see that this property holds the other way around as well. Right. So if you take the multiplication of the Fourier series coefficients of two signals, then in the time domain, right, the corresponding time domain signal will be equal to the convolution of these two signals. Okay. So multiplication in the time domain corresponds to convolution in the Fourier series coefficients. And similarly, the other way around, multiplication in the Fourier series coefficient corresponds to convolution in the time domain signals. Okay. Now, these differentiation and integration are also very important, but we did not show them here. You could also show them directly following the straightforward computations that we just did. Okay, and we're going to use this later on when we talk about systems with, well, actually, we'll talk about them in examples coming up, but also when we talk about systems described by differential equations. Okay. Now we also looked at this conjugation, real and even, real and odd signals, and most importantly, we looked at this Parseval's relation. Okay. Now let's look at a few examples. Okay. So again, the reason for looking at these basic properties of Fourier series coefficients is because, through by first obtaining the results for these, basic operations, we will be able to, more quickly obtain the results for more complicated scenarios. Okay. So here in example 3.6, we're looking at the case of, we're hoping to find a Fourier series representation of g of t that is equal to x of t minus 1 plus 1/2, where x of t is defined in example 3.5. Okay. So example 3.5 is the case of periodic square waves. Okay. This is the case of periodic square waves. But for the particular example that we're looking at, here we will have t1 equal to 1 and capital T, which is the period, equal to 4. Okay. So here, the x of t we're looking at is the same as example 3.5, but with t1 equal to 1, right? You can see that starting from the center extends to the left and right by 1, and with period equal to 4, right? You can see that this repeats itself after time 4. Okay. So with period 4, the fundamental frequency omega naught is 2 pi over capital T, which is pi over 2. Right? Okay. So to find the Fourier series coefficient for g of t, right, by linearity, we know that we can start out by finding the Fourier series coefficient for this term plus this term. Okay. And the Fourier series representation of this term corresponds to the time-shifted, the Fourier, okay, so this term is the time-shifted version of x of t, and we also showed the Fourier series coefficient for a time shift in the signal. Okay. So in particular, if x of t has a Fourier series representation denoted by ak, okay, then by the time shifting property, we know that x of t minus 1 has a Fourier series representation bk equal to ak e to the minus jk 2 pi over capital T. Okay, so this is given over here, right? So here T naught is 1, right? So we have, ak e to the minus jk 2 pi over capital T, which is pi over 2 in our case, times 1. Okay. Okay. Now for the second term, minus 1 over 2, right? This is just a constant term, right? So there are no higher frequency components. Okay. So if you compute its Fourier series coefficients, you'll find that you only have a value minus 1 over 2 for k equal to 0 and 0 for all other k. Okay. So then by linearity property, we know that the Fourier series coefficient of g of t will be equal to the Fourier series coefficient of x of t minus 1 plus minus 1 over 2. Okay, so by linearity property, we know that g of t, which is equal to x of t minus 1 minus 1/2, should have Fourier series coefficient equal to bk plus ck. Okay, and if you combine this, bk plus ck is equal to, right, so this is equal to a0 minus 1/2 for k equal to 0, okay, and ak times e to the minus j k pi over 2 for k not equal to 0. Okay, so for k equal to 0, ck is minus 1 over 2, and bk for k equal to 0 is just a0 because this term becomes 1. Okay, now you can further write this. Okay, you can further substitute the values of a0 and ak from the Fourier series representation of this periodic square root, okay, that we derived before. So from this example 3.5, we showed that, you know, a0 is just 2 over t1 over t. Now in our case, t1 is 1, capital T is 4, so this is 1/2. And here ak is just again 1/2 sine 2 pi over capital T k t1. Right, t1 is 1, capital T is 4, so 2 pi over capital T is again pi over 2. Right, so substituting these parameters inside, I can get a0 and ak. So in this case, a0 is 1/2. 1/2 minus 1/2 is 0. Okay, and ak here is sine pi k over 2 over k pi e to the minus j k pi over 2. And this is for k not equal to 0. So you can see from this example that by applying first the time shifting property and then the linearity property, we can easily obtain the Fourier series coefficient for g of t with knowledge of the Fourier series coefficient of the periodic periodic square wave x of t. Okay, so using these properties, we can obtain the Fourier series coefficient of some slightly more complicated signal g of t using the Fourier series coefficient of a more simple case that we derived before, which is that of x of t. Now, in the next example, we do this again, utilizing results that we obtained for g of t. So in this example, we're looking at x of t that is equal to this periodic triangular wave. Okay, so you can see here again that the signal is periodic with period 4, and therefore the fundamental frequency is again pi over 2. Okay, now let us denote the Fourier series coefficients for x of t as, let's say, ek, okay? All right. And suppose that we set this g of t that we obtained in the previous example, okay, as something with Fourier coefficient dk. Okay. Now notice that g of t is actually equal to the derivative of x of t. Okay. So you can see that for t from 0 up to 2, okay, for x of t from 0 up to 2, the derivative is minus 1/2. Okay. And for t from 2 up to 4, the derivative of x of t is minus 1/2. Okay. So indeed, g of t is equal to the derivative of x of t. Now, by this property here, we know that if you have a signal that is equal to the derivative of x of t, then the Fourier series coefficient of this signal, this new signal here, will be equal to jk omega naught times the Fourier series coefficient ak of the original signal x of t. Okay. So in our case, the original signal has Fourier series coefficient ek. Okay. So therefore, dk is equal to jk omega naught ek. Okay. And omega naught here is pi over 2. So this is just jk pi over 2 ek. Okay. Now for k not equal to 0, okay, I can divide this jk pi over 2 to the other side so that ek is equal to dk divided by jk pi over 2. Okay. And this dk we just derived in the previous example, right? So this dk is this expression here, right? So therefore, this is given by okay, so for k not equal to 0, it is this thing here. So this is given by, if I bring this 2 up here, I get 2 times sine pi k over 2 over j k pi squared e to the minus j k pi over 2. Okay. And for k equal to 0, right, for k equal to 0, E0 is just equal to the average of the signal over one period. Right, so this is just x of t dt over one period, which is 1/2. Okay. So using our knowledge of the Fourier series coefficient of g of t, And by applying the property for differentiation, we readily obtain the Fourier series coefficient for this x of t, whose derivative gives you the signal g of t in the previous example. Okay. Now let's move to this next example, which is called a pulse train. Right. So here you see that x of t is equal to a delta function equally spaced by capital T. Okay, the summation of delta functions or impulses equally spaced by capital T. Right. So it is something that looks like this. Okay. So this signal here is sometimes called a impulse train. Okay. Now you can see that this is a periodic signal, right? Periodic with period capital T. So you can write it in terms of its Fourier series representation with the set of harmonically related complex exponentials that are all period with period capital T. Okay. And the coefficients AK you can obtain by 1 over t, the integral over one period. Let's say we take minus t over 2 to t over 2. This function delta of t. Oh, well, actually, okay, this would be x of t e to the minus jk 2 pi over capital T dt. Okay, but over this one period, x of t is just delta of t. Okay, so I can replace this with delta of t okay, and when you take the integral over this, right, you have this inside is non-zero only when t is equal to 0. So when you substitute equal to 0, this is 1. So the integral of this is just capital T divided by capital T is 1. Oh, sorry. Sorry. Okay. So like I said, this inside is non-zero only when t is equal to 0, right? So when t is equal to 0, this becomes 1. So you have 1 over t, t over 2 minus t over 2, delta of t dt, right? So I'm substituting 1. I'm substituting this with 1 because it is non-zero only when t is equal to 0. Okay. And then the integral over a delta function, it has unit energy, unit area, right? So this integral is 1. So we get AK equal to 1 over t. And this is true for all k. Okay? So this is saying that I can express x of t as 1 over t e to the jk 2 pi over capital T t for k from minus infinity to infinity. Okay? Or you can bring the 1 over t outside since it is the same for all k. Okay. All right. Now, suppose we revisit the problem of finding the Fourier series representation of this periodic square wave. Okay. So suppose you're asked to find the Fourier series coefficients of the signal g of t. Okay. Now this signal g of t, although it may not appear so obvious at first sight, but this signal g of t is actually inherently related with the impulse train that we just described. Okay. And this is because if you take the derivative of g of t, you will get a signal q of t that is equal to the summation of two impulse trains. Okay. So if you look at this, you will realize that this q of t, which is the derivative of this periodic square wave, is equal to the summation of two impulse trains, one shifted to time minus t1 and the other shifted to time t1. Okay. So you have x of t plus t1, where this x is the impulse train that we gave on the previous slide, minus x of t minus t1. Okay. Now, by letting the Fourier series coefficient of q of t be denoted by, let's say, bk. Okay. Then this means that bk should be equal to, okay, should be equal to this ak times a phase shift because of the time shift in the time domain signal. Okay, so this bk should be e to the j k omega naught t1 because of this time shift times ak, which is the Fourier series coefficient of this impulse train. And similarly for the second term, I have a phase shift e to the minus j k omega naught t1 times ak again, which is the Fourier series coefficient for the impulse train. Okay. And then if I substitute this ak inside, I will get 1 over t 2j sine k omega naught t1. Okay, so if you recall, ak is this 1 over t, and these two complex, the subtraction of these two complex exponentials give you 2j sine k omega naught t1. Okay. Now, by letting the Fourier series coefficient that we want to find be denoted by ck. Right, so here our goal is to find the Fourier series coefficient of g of t, which we denote by ck. Okay, so we know that q of t is the derivative of g of t. So this means that bk should be equal to jk omega naught ck. So therefore, again, for k not equal to 0, we can write ck as bk over jk omega naught. Okay. And by substituting bk inside, I get 2j sine k omega naught t1 over j k omega naught capital T. Okay, so the j cancels out, and if you substitute omega naught with 2 pi over capital T, okay, then you have in the denominator pi k, and in the numerator sine of k omega naught t1. Okay. And then for k equal to 0, okay, so for k equal to 0, we have simply C0 that is equal to the average of the signal, right, over one period. Okay, and this is simply 2T1 over capital T. Okay. So if you compare with the result that we obtained for example 3.5, you will see that this is the same as we obtained there. Okay, so this is just an alternative derivation to example 3.5. Okay. Now in this last example, we can show, we want to show that, just by specifying certain properties of this continuous time periodic signal, we often can, evaluate or find this signal explicitly. Okay. So here we're looking at the case where we are given 5 properties of this signal. Right? First of all, the signal is real. Okay. Secondly, the period is 4 with coefficient, with Fourier series coefficient AK. The third property is that AK is 0 for k greater than, with absolute k greater than 1. So this basically means that there are only 3 non-zero Fourier series coefficients, right? This basically means that only a minus 1, a0, and a1 are non-zero. Okay. Now, we know also by the fourth property that the signal with Fourier series coefficient bk, which is equal to this relation with AK, is an odd signal. Okay. And the last property tells us that the average of the signal power, okay, over one period is 1/2. Okay. Now we can look at these properties one by one. Right. So first of all, by the second property, we know that the signal has period t equal to 4. So this means that the fundamental frequency, which is 2 pi over t, is just pi over 2. Okay. And also, by property 3, okay, we know that there are only 3 non-zero Fourier series coefficients. So this means that x of t will be equal to a0 plus a1 times e to the j, okay, omega naught t, where omega naught is pi over 2, plus a sub minus 1 e to the minus j pi over 2 t. Okay. Now, furthermore, by the first property, we know that the signal x of t is real, right? So by 1, x of t is real. And thus, ak is equal to a minus k complex conjugate. Right, so this is saying that the signal must be conjugate symmetric. So if you apply this to A1, right, you will see that A sub minus 1 is just A1 complex conjugate. So if you substitute this property inside, this is saying that x of t is A0 plus this times its complex plus its complex conjugate, which gives you the real part of A1 e to the j pi over 2t, 2 times. Okay. Now we have used properties 1, 2, and 3, right? Now what about property 4? Property 4 is a little bit tricky. Okay. So now we're looking at a signal whose Fourier series coefficient is this e to the minus j pi k over 2 times a sub minus k. Okay. So if you first look at a sub minus k, right, what signal will have a Fourier series coefficient that is equal to a time reversal of the Fourier series coefficient of x of t? Okay. So we showed that this holds for the time reversal of the signal. Right. So here we showed that the time reversal of x of t has Fourier series coefficient a sub minus k. Okay. Okay. So a sub minus k corresponds to the Fourier series coefficient of the time reversal of x of t. Okay. And then e to the minus j pi k over 2, okay, is a phase shift in the Fourier series coefficient, which corresponds to a shift in time of the original signal. Okay. So by 4, we know that the signal corresponding to the Fourier series coefficient bk is this x of minus, right, the time reversal of t shifted by 1. Okay, so this minus t is inferred from this a sub minus k, and the time shift by 1 is inferred by this phase shift here. Okay, so if you get rid of this bracket inside, you have x of minus t plus 1. And property 4 tells us that this signal, x of minus t plus 1, is odd. Okay. And since x of t is real, this signal must be real as well. Okay. So this signal is real and odd. Okay. So if this signal is real and odd, then this means that the Fourier series coefficient must be purely imaginary and odd. Okay. So therefore, bk must be purely imaginary and odd. Okay. So being odd implies that B0 must be 0 and that B1 is equal to minus B sub minus 1. Okay. Now moving on to the last property, right? The last property tells us that the average power over one period is 1 over 2. Okay. So by 5, okay, we know that the average power over one period, okay, which is also the average power of the time-shifted reversed signal x of minus t plus 1 squared, okay, is equal to 1/2. Okay. So by Parseval's theorem, we know that the average power over one period is equal to the sum of the power of all of the harmonic components. Okay. So by Parseval's relation, okay, we know that B1 squared plus B minus 1 squared, which are the only two non-zero Fourier series coefficient for this delayed time reversal signal, is equal to 2 times B1 squared because it is odd, which is equal to 1/2. Okay. So this implies that B1 should either be J over 2 or minus J over 2, since it must be pure imaginary. Okay. Now by this property 4, we can then, with B, we can then obtain the value of A. Okay. So by this property 4, we know that A1 should be e to the minus j pi over 2 B minus 1. Okay. And this term up here, right, is just minus j. Okay, so this is minus j b sub minus 1, and by the odd property of the coefficients b, this is also j b1. Okay, and similarly, a sub minus 1 is e to the j pi over 2 b1, which is j b1. Okay. So we know that a1 square plus a minus 1 square should be equal to 2 times b1 square, right? So we're substituting these inside. We know that this is equal to 2 times b1 square, which is equal to 1/2 by the above. Okay. But we also know that this, right, by Parseval's theorem, this 1/2 should also be equal to, the sum of the harmonic components. Okay. So this means that A0 is 0. Okay. Now there are two possible solutions for B1. Okay. So for B1 equal to j over 2, we have A1 equal to minus 1 over 2, okay, which is equal to A sub minus 1. Okay, and therefore, if you substitute this inside, you will get that inside the Fourier series representation, you will get x of t equal to minus 1/2 e to the j pi over 2t plus e to the minus j pi over 2t. Okay, and this is minus cosine of pi over 2t. Now, if you choose the solution of B1 equal to minus j over 2, then we have A1 equal to 1/2 equal to A sub minus 1. And in this case, x of t would be cosine pi over 2t. Okay. So in this example, we showed that by specifying certain properties of the signal and its Fourier series coefficients, we are able to infer what this signal is. Okay, and in this particular example, we can infer this signal up to a sign, up to a plus and minus sign. Okay. So again, if going through this list, right? So we started out by looking at property 2, which tells us that the signal is periodic with period 4. Okay, so the fundamental frequency is pi over 2, and by 3, we know that there are only 3 non-zero. There can only be 3 non-zero Fourier series coefficients: A0, A1, and A minus 1. So x of t can be expressed in this form. So what remains to be determined is the coefficients for A0, the values for A0, A1, and A minus 1. Okay. Now, by property 1, we know that x of t is real, so the Fourier series coefficients are conjugate symmetric. So if you substitute this inside, x of t is equal to, can be written more concisely as this, right? So it's actually determined by only two coefficients, A0 and A1. Okay. Now, by this property 4, we know that a signal with Fourier series coefficient equal to this is odd. Now, what is this signal, right? So we see here that a signal with Fourier series coefficient a sub minus k should be the time reversal of the original signal x of t, and this further imposes a time shift. So the signal corresponding to this Fourier series coefficient should be x with the time reversal shifted by 1, or in other words, x of minus t plus 1. And we know that this signal is real and odd by this first and fourth property. So if the signal is real and odd, then its Fourier series coefficient must be purely imaginary and odd, which means that B0 must be 0 and B1 is equal to minus B sub minus 1. Now next, we still need to apply this last property, which is saying that the average power over one period is 1/2. Now by Parseval's theorem, we know that this 1/2 should be equal to the sum of the Fourier series coefficients of B, and also should be the sum of the Fourier series coefficients of A. Okay. Now we can see that the Fourier series coefficients of A1 and A minus 1 have energy already equal to 1/2, and therefore A0 must be 0. So applying all these properties, plugging this inside either this equation or this equation here, we can find that x of t reduces to minus cosine pi over 2t if b1 is j over 2, and cosine pi over 2t if b1 is minus j over 2. Okay, so yesterday we, including last week, we talked about the convergence of Fourier series representation. Okay, so in particular, in continuous time, right, when we're looking at periodic continuous time signals, we want to see when the convergence of this, summation as capital N goes to infinity, converges to the actual periodic signal x of t. Okay. Now we showed, under different notions of convergence, that almost all practical signals that we may encounter in practice would have a Fourier series representation, right? Periodic signals, I would say. Okay. So then, given the fact that most periodic signals can be written in terms of its Fourier series representation, we can then go on to analyze or compute the Fourier series representation for different types of signals, different signals. Okay, so then we looked at some common properties of these continuous time Fourier series. That gives us basic formulas for computing the Fourier series for basic operations such as addition under the linearity property, right? Time shifting, time reversal, time scaling, multiplication, conjugate symmetry, and so on and so forth. Okay, so with knowledge of these. Of the Fourier properties of the Fourier series under these basic operations, this will help us, compute the Fourier series representation for more complex signals, right? So if you have complex signals that can be decomposed into these basic operations, then through this table, you should be able to derive or compute the Fourier series representation for the complex signals much more easily, okay? And this is what we did for these few examples here, right? So, for example, in this 3.6, we were looking for the Fourier series representation of g of t, which is equal to the sum of x of t minus 1 minus 1/2, where x of t is the periodic square wave that we looked at in example 3.5. So by linearity property, we know that the Fourier series coefficient of g of t will be equal to the Fourier series coefficient of x of t minus 1 plus that of minus 1/2. Okay, and the Fourier series coefficient of this x of t minus 1, right, which is a time-shifted version of x of t, would then be the same Fourier series coefficient times a phase shift. Okay, so following procedures similar to this, we can utilize the properties that we showed to help us derive the Fourier series representation of more complex signals. So we did the same here by identifying the fact that the derivative of x of t gives you the g of t we showed on the previous page. Okay. All right. So that's regarding the continuous time case. Now today we want to move on to the discrete time case. So the same discussion can be done also for the discrete time case as well, right? So now suppose that we're looking at a periodic discrete time signal x of n that is periodic with period capital N. So what this means is that x of n will be equal to x of n plus capital N for all n. For a signal, right, that is periodic with period capital N, we're interested in looking at whether or not it can be represented by a set of harmonically related complex exponentials with the same period, capital N. Okay. Now, if you recall, when we discussed this, the set of harmonically related complex exponentials, this is what we gave before, right? So for the set of harmonically related complex exponentials with period capital N, the functions would be equal to, e to the j k 2 pi over capital N times n, right? Where if you define 2 pi over capital N as the fundamental frequency omega naught, you can then write it as e to the j k omega naught n, right? And this is for all k, all integers k. Okay. But what's different from the continuous time case is that in the discrete time case, there are only finite number of distinct signals in a set of harmonically related complex exponentials. Okay, so in fact, if your period is capital N, then there are only n distinct signals in this set. Okay, because once you go to once you increase the index by capital N, you will get back the same function as that of the index k. Okay, so this is simple to prove, right? We proved this previously. If you substitute k plus capital N inside here, you will see that there will be a additional 2 pi term that comes out, which will be equal to 1, right, with the exponent, right? So exponential to the power j2 pi is equal to 1. So in the discrete case, we're interested in periodic signals that can be represented by a linear combination of this set of harmonically related complex exponentials. Okay, in particular, that is the signal x of n that can be written as a linear combination of these harmonically related complex exponentials. Okay, and this phi k here is e to the j k omega naught n for omega naught that is equal to 2 pi over capital N. So if you substitute that inside, this is what you get. Okay, so this is the discrete time Fourier series, similar to what we get in continuous time. But the key difference here, okay, the key difference here is that, there are only finite number of distinct signals in the set of harmonically related complex exponentials in the discrete case. So instead of summing over all possible values of k, right, it is sufficient to sum only over capital N consecutive values of k. Okay, and this is denoted by this symbol here. Okay, so this denotes the set of n consecutive integers. Okay. So to apply this, discrete time Fourier series representation, right, there are two questions that you need to ask first. Right? So first of all, you need to determine when a signal x of n can be represented in terms of its Fourier series representation. Right. So in continuous time, we spent a lot of time talking about this, right? So in the continuous time case, right, it's very hard to have exact convergence, right? Convergence over all points of the function, convergence of the of the Fourier series representation to x of t at all points of the function. So we considered other notions of convergence, such as convergence in the sense of having vanishing error energy, or convergence in terms of convergence almost everywhere except at isolated points of discontinuity, okay, which is specified by the Dirichlet conditions. Okay, so there's the same question here, right? What signal x of n has a Fourier series representation? Okay, so when you say that a signal x of n has a Fourier series representation, it means that you must be able to write it as a linear combination of these complex exponentials. Now, each one of these complex exponentials are periodic with period capital N. So the linear combination of them must also be periodic with period N. Okay, so the first thing is that x of n needs to be periodic with period N. Okay, so to answer this question of determining if xn has a Fourier series representation, you should note that first of all, xn must be periodic with period N. Okay. But then the question is, are all signals that are periodic with period N, does all signals with period capital N have a Fourier series representation? Okay. So does all xn with period N have a Fourier series representation. Okay. Now this is equivalent to asking, is there a solution to the set of coefficients AK, right, for, K in some consecutive value of N, such that this equation holds for, N over a consecutive range of values. Okay, in particular, let's say such that x0 is equal to summation AK, x1 is equal to summation AK times e to the j 2 pi capital N K, so on and so forth, up to x of n minus 1 summation e to the j 2 pi capital N K n minus 1. So asking whether or not any signal xn with period capital N have a Fourier series representation is equivalent to asking whether or not there is a solution to AK such that this system of linear equation holds for any choice of values x0 to xn minus 1. Okay, for any. And the answer to this question is yes, right? Because what we have here, right, you can show that the capital N equations that you have here are linearly independent. Okay, so when you have capital N unknowns, right, you have capital N equations, linear equations, to solve capital N unknowns. Right, there must be a solution if the equations are linearly independent. Okay. So the answer is yes. Okay, since the equations are linearly independent. Okay. Do we have any questions about this part? Right. So different from the continuous time case, the existence of a Fourier series representation is much simpler to show in the discrete time case. Because if you want to show whether or not an expression of this kind, a representation of this kind holds for any periodic signal x of n, you only need to see if there exists a sequence of a set of coefficients, let's say a0 to a capital N minus 1, such that this equality holds for for any consecutive values of n. Okay, and this is true because the capital N, linear equations that you get will be linearly independent. Right. So now we have established the fact that any periodic signal in discrete time has a Fourier series representation. Okay, so there would be no exceptions, like in the continuous time case. Okay, but then how do we find the values of the Fourier series coefficients? So the procedure is also similar, right? To determine the Fourier series coefficients, we also utilize the fact that if you sum a complex exponential over, one period, capital N, right? So if you sum this complex exponential over one period, then this summation must be 0, right? So if you recall, we talked about this previously. You can view a complex exponential as, sinusoids, right? So if you sum samples of a sinusoid, over one or more periods, then the summation must be equal to 0 because the positive part cancels out with the negative part, okay? The only exception is when k is equal to 0, because when k is equal to 0, this exponential is just equal to 1. So you would be summing over capital N ones, and therefore the summation is equal to capital N, okay? So by utilizing the fact that this summation of complex exponentials is equal to a capital N if k is 0 or some integer multiple of capital N and 0 otherwise, right? We can then compute the Fourier series coefficients by multiplying both sides by the corresponding, by the complex conjugate of the corresponding complex exponential. Okay, so for example, suppose we pick this e to the minus jr 2 pi over capital N. We multiply this on both sides so that we get xn times e to the minus jr 2 pi over capital N. We sum this over one period of n. And on the right-hand side, right, we have the Fourier series representation, which is ak e to the j k, but now minus r 2 pi over capital N, and again summing n over one period. Okay. So if you sort of switch the order of summation, you can write this as summation k ak summation n e to the j k minus r 2 pi over capital N. Okay. Now, if you look at this summation, you can see from the above property that this summation is 0 for all k not equal to r, right? Or that this summation is equal to, is non-zero and equal to capital N only if k is equal to r. Okay. So this reduces to AR times capital N, okay? Well, this should hold for all R, that are integer multiples of capital N, right? So, or, AR plus some integer multiple of capital N. Okay. So if you divide capital N to the other side, then you find that AR is 1 over N summation xn e to the minus jr 2 pi capital N summing n over one period. Okay. So again, if you're acquainted with linear algebra, you can view this as taking the inner product, okay, between our signal and the corresponding complex exponential. Okay. Right. So this gives you the discrete time Fourier series pair, similar to what we have in continuous time.
老师，
是
那个可以问一下问题吗？
可以。
上页这边就是你可以在就是那个 ARN 上，就是怎么变这个的？就是当 k 不等于 r 的时候嘞。
k 不等于 r 的时候，这个 summation 就是等于0。OK， 所以这一个东西，它就是说，它会等于 n when k is equal to r and 0 when k is not equal to r。OK。
那个下面那个写 AR 加 LN 是吗？是 L 吗？
对，就是任何 integer multiple of capital N。
好，谢谢老师。
OK。好，还有没有其他问题？
老师，
请说。
就是为什么那个这上面，为什么 k 等于正负 n 跟正负2n 的时候，它的 summation 也会等于大 N？
因为我们现在在看的这些是，就說是周期是大 N 的 complex exponential， 所以 e to the j k 2 pi over capital N， N 这是一个周期是大 N 的 complex exponential， 所以你如果说，比如说，就说我 n 加大 N 的话，这一个就会回到它自己。Okay， 就是比如说，你原本是 e to the j k， 这个2 pi capital N， OK， 那假设你 sum over 一个周期 ，OK， 那就是说你想象，如果说你这个 k 是带0的话 ，OK， 你带0的话，这个就是exponential 0嘛，对不对？
可以理解。
那你如果带大 N 的话，它就是 exponential 这个 j 这个2 pi n， 对不对？那2 pi 任何整数倍的2 pi 也就等于是0。
好，可以，谢谢。
可以理解吗？OK。所以这边其实 discrete time case is almost exactly the same as the continuous time case. Okay, so I went a little bit faster because everything is the same, right? But I would say, the key difference with the continuous time case is that in the continuous time case, you would be summing from -infinity to infinity, because if you're looking at a set of harmonically related complex exponentials with period capital T in the continuous time case, this set has infinite members, okay? But in the discrete time case, there are only a finite number, in particular capital N, distinct signals in this set of harmonically related complex exponentials, okay? So if you sum beyond capital N consecutive values, you will be, summing over, the same signals repeatedly. So because of this, finite summation, the existence of the Fourier series representation is then much easier to show, right? In fact, as long as you are able to find these, coefficients for any possible, set of capital N consecutive values of x, you can say that the Fourier series representation exists. And in fact, this solution must always exist because these linear equations are linearly independent. Okay. So once we establish the existence of Fourier series representation, we can then obtain the desired Fourier series coefficient by taking the inner product between the signal and the corresponding complex exponential that we're looking at. So this gives us this discrete time Fourier series pair. So given the Fourier series coefficient and the period capital N, we are able to construct or synthesize this signal xn, right? So this equation above is often called the synthesis equation, okay? And given the signal xn, you can also extract out the component for each harmonically related complex exponential. So this is called the analysis equation. Okay, so it's the same for the terminology is the same for continuous time as well. Okay. So again, I want to emphasize that the summation here is over any arbitrary set of capital N successive values of k. Okay. So you could be summing k from, let's say 1, 2, 3 up to capital N, right? Or you could be summing over k that is equal to, let's say 3, 4, 5 up to n plus 2, right? N plus 1, n plus 2. Okay, so summing over any consecutive capital N consecutive values would be sufficient for this summation. Okay. Now the reason for this is because when you go beyond a range of n consecutive values, these terms become start to repeat itself, right? Start to repeat itself. So sometimes for convenience, we would like to view the sequence of these Fourier series coefficients as an infinite sequence that is periodic with period capital N. Okay, so even though each time we utilize this synthesis equation, we're only taking capital N consecutive values of these Fourier series coefficients. But if you view this as an infinite sequence of Fourier series coefficients, then what you have is actually a periodic sequence. Okay. All right. Now let's look at a few examples. Okay. So here we have the example of xn equal to a pure sinusoid sine omega naught n. Okay. Now this you can view as the sampling of a continuous time sinusoid at integer points in time. Okay, so you can view this as sampling x of t equal to sine of omega naught t at integer values of t. Okay. Now, if you recall, right, samples of a continuous time sinusoid may not necessarily be periodic, right? You need to sample, at, specially chosen intervals in order for this signal to be periodic. Okay. So this signal, if you recall, would be periodic only when 2 pi over omega naught is an integer or a ratio of integers. Okay. Right. So as we showed previously, only in this case will your samples be able to, come back to some value that occurred before. Okay. Now here we first look at the case where omega naught is equal to 2 pi over capital N, right? Or if you like, you can view this as having, 2 pi over omega naught equal to, capital N, right? Which is an integer. So in this case, this is a periodic signal with fundamental period that is capital N. Okay. So in this case, we know that we can represent x of n as a linear combination of the set of harmonically related complex exponentials with period capital N. Okay. So in fact, you can see this easily by, by applying Euler's relation to decompose this sign. Okay. So in this case, this xn, you can split into 1 over 2j e to the j 2 pi capital N n minus 1 over 2j e to the minus j 2 pi capital N n. Okay. All right. Okay. So if you were to write out, x of n in terms of the general expression for the series, Fourier series representation, this would be summation of ak e to the jk So this would be summation ak e to the j k 2 pi over capital N n. Okay, summing k over one period. Okay, so if you compare the two, you will find that this is essentially A1, right? The term corresponding k equal to 1. Okay, and this corresponds to a sub minus 1, which is minus 1 over 2j. Okay, so if you plot this out, okay, you'll get something like this. So suppose this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 2, 3, 4, 5, 6, 7, 8, 10. Okay, so this is 1, this is minus 1, right? So we have okay, sorry. So we know that A1 is 1 over 2j, A minus 1 is minus 1 over 2j, and all the other AKs are 0. Okay. So if you plot this out, A0 is 0, A1 is this 1 over 2j, A minus 1 is minus 1 over 2j. Okay. Now this, suppose we're looking at the case where, let's say, for example, we're looking at the case where n is equal to 5, okay? So that these coefficients should repeat themselves after, you know, any integer multiple of capital N, okay? So if you move this by 1, 2, 3, 4, 5, you would again get 0 here, and minus 1 over 2j here, and a 1 over 2j here. Okay, so all others are 0. So similarly on this side, right, you have 0, 0, 1 over 2j, 0, minus 1 over 2j, 0, 0, so on and so forth. Okay. Okay. Now let's look at another case. Right. Now suppose that in this case we have omega naught equal to 2 pi capital M over capital N. Okay. And let's assume that M and N have no common factors. Right. So suppose that they are coprime. Okay. So when they have no common factors, then we showed previously that this signal would just have period. The fundamental period of this, fundamental period of this signal would be capital N. Okay. So if the fundamental period is capital N, we again want to represent it using the set of harmonically related complex exponentials with period capital N. Okay. Now you can also do this easily by decomposing this sine function. So again, xn can be written as 1 over 2j e to the j 2 pi capital M over n minus 1 over 2j e to the minus j 2 pi M over n. Okay. Now again, we hope to write this in terms of this general Fourier series representation for k in consecutive values. Okay, so if you compare the two, you'll see that 1 over 2j corresponds to the case where k is equal to capital M. So in this case, M is equal to 1 over 2j, and A sub minus M is equal to minus 1 over 2j. Okay, and again, AK is equal to 0 for all k not equal to plus or minus m, okay, or integer multiples of that, or integer, okay, multiples of n. All right, so I should make the same notion here, right? So plus any integer multiple of capital N. Okay. So for example, suppose we look at the case where m is equal to 3 and n is equal to 5. Okay. Now, when m is equal to 3 and n is equal to 5, right? This would be a3 and this would be a minus 3. Okay. But a3 and minus 3 are beyond the range of 5 consecutive indices. Okay, so instead of looking at a sub minus 3, right, we want to look at an index that is within the range around a3. So this would be minus 3 plus capital N, which is 5, which gives you a2, right? So a2 is minus 1 over 2j, and a3 is equal to 1 over 2j. So if you plot this out, okay, you will see that you should have 1 over 2j at 3, right? So you have this 1 over 2j here. You should have minus 1 over 2j at a2, okay? And since the period is capital 5, this repeats itself every integer multiple of capital N, right? So let's say 1, 2, 3, 4, 5, right? You have this minus 1 over 2j here, 1 over 2j here, right? All others are 0. Right, then again, 1, 2, 3, 4, 5. Right, all these are 0. Oops. Okay, and so on. Okay. Okay, so do we have any questions about this example?
老师听得到吗？
可以，请说。
老师，我可以问一下，为什么 A-3 跟 A2 是为什么会跑出一个 A2 啊？对，
因为这个 index 它就是每隔大 n 等数每隔一个大 n 就会开始重复。
嗯哼。
对，因为这个 AK 会等于这个 AK 加大 N， 所以如果 K 取负3的话，那负3加5就是 A2， OK， 所以 A7 A12都是负1 over 2j 这样。
OK， 好，谢谢老师。
对。所以你如果说if you view the entire sequence of Fourier coefficients, if you view the sequence of Fourier coefficients as a sequence of values with indices going to infinity, then what you have is a periodic sequence. Okay, but when you want to synthesize the signal xn using a linear combination of complex exponentials, you would only be taking capital N number of terms, right? Because beyond a range of capital N, right, these complex exponentials and their coefficients start to repeat themselves. Okay, so in practice, when you try to write out the synthesis equation, you're always only looking at let's say you're always looking at 5 consecutive values of the coefficients. Let's say 1, 2, 3, 4, 5. Right? You're only looking at a window of n equals to 5 coefficients. Okay? Now any window is okay, right? You could also be looking at some window like this, right? That's also okay, right? Or you could be, looking at some window like this. Okay, so any window of 5 consecutive values, of coefficients is sufficient for you to write out the Fourier series representation. Now let's look at one more example. This is the case where xn is equal to the sum of these sinusoids. Okay. So this is 1 plus sine 2 pi over capital N times N, 3 cosine 2 pi over capital N times N, cosine 4 pi over capital N times N plus pi over 2. Now you can see that all of these signals are periodic with period capital N. Okay, so overall, this signal has period, okay, capital N. So you hope to be able to represent this using a Fourier series representation using the set of harmonically related complex exponentials that have period capital N. Okay, so you hope to write this as summation ak e to the j k 2 pi over capital N n for k summing over 1 period. Okay, so to find these coefficients ak, we can again apply Euler's relation to split up these sinusoids. Okay, so this gives us 1 plus 1 over 2j e to the j 2 pi capital N n minus e to the minus j 2 pi capital N n, okay, plus 3 over 2 e to the j 2 pi capital N n plus e to the minus j 2 pi capital N n, okay, plus 1/2 e to the j pi over 2, because of this face pi over 2 here, e to the j 4 pi capital N n plus e to the minus j pi over 2 e to the minus j 4 pi over 2 over n capital N n. Okay. So if you compare this expression with the desired Fourier series representation above, right, you can see you can derive the corresponding values of AK, right? So in particular, A0, right, corresponds to the constant term, which is 1, right? A1 corresponds to the term e to the j 2 pi capital N, right? And we can see that this appears here and also here, okay? So we have 1 over 2j plus 3 over 2, okay? And you can write this, moving j to the numerator, you have 3 over 2 minus 1 over 2j, okay? Now for the term a minus 1, for k equal to minus 1, this corresponds to the term e to the minus j 2 pi capital N, which appears here and here, okay? So this, following similar procedures, we can write this as 3 over 2 plus 1 over 2j, okay? Now looking at A2, A2 is the case where k is equal to 2. So this is e to the j 2 times 2 pi is 4 pi, right? E to the j 4 pi over capital N, which appears here. So the Fourier series coefficient here is 1/2 e to the j pi over 2, right? E to the j pi over 2 is just j. So this is 1/2 j, okay? So similarly, right, for this term, you get a minus 2 equal to minus 1 over 2j. Okay? So you can sort of see here that, similar to the continuous time case, you can observe that the Fourier series coefficients are conjugate symmetric with each other, right? You can see that A1 is A sub minus 1 complex conjugate, right? Because there is this sign difference in the imaginary term, right? And A2 is equal to the complex conjugate of A sub minus 2, right? So, notice that AK is equal to A sub minus K complex conjugate. And when does this hold, right? So you can show that, similar to the continuous time case, this holds when your signal xn is real, okay? So this holds in general for xn that is real, okay? Now, in this example, we see that each individual term has period capital N. So when you sum them up, the signal xn also has period capital N. Okay. Now, let me ask a extending question. Right. So what if the last term is replaced with cosine 3 pi over capital N plus pi over 2. Okay. So in this case, okay, so well, maybe I can ask somebody here. 庄敏勋在吗？
喂，有听到吗？
喂，嗨。所以如果说我把最后这个 term 换成这个 cosine 3 pi 而不是4 pi 的话，会有什么问题吗？
会多出一个讯号吗？
怎么说呢？
就是在用 Euler 的时候会不能跟前面的合在一起。
OK， 所以你刚才说为什么不能合在一起？
我看一下。就是，好像不会。是它的讯号会数值会变吗？
我可以给一个提示，就是说，这个 cosine 3 pi over capital N 这个它的周期是多少？
周期。
它的周期会是这个 capital N 吗？
应该是。应该是。
OK， 就是你想想看，你如果说带 n 等于0，然后再带 n 等于大 N 进去的话，或许那不是一个很好的例子。就是说如果你带这个 n 等于1跟大 N 加1进去的话，你得到的值会一样吗？
不会。
不会嘛，对不对？OK， 好，所以这是有一点难的问题，对，所以就说这个一时间回答不出来是蛮正常的。对，我再看看其他同学有没有办法再进一步那个傅晓彤在吗？
在。
OK， 所以刚才有提到就是说这个 cosine 新的这一项下面这一项它的周期就不再是大 N 了不再像上面这原本这一项是大 N， 那这时候怎么办？你还可以写成上面的这个形式吗？
不行。
不行，为什么？
我不知道
不知道 ，OK， 好，没关系。对，这个问题就是一个比较难的问题，所以小时候让大家回去思考一下这样。那我想其实关键就是在于说，你要能够写成上面的这个 Fourier series representation 其实代表的是你的这个讯号 xn 必须要是有周期大 N 的一个讯号因为它是周期大 N 的讯号，你才会用周期是大 N 的这些harmonically related complex exponential 去组成它。 那现在如果你混两个 cosine， 它的周期是不一样的话，那你就必须要去找到它的共同周期。OK， 然后你的 Fourier series representation 就应该是以那个共同周期，也就是会是 xn 的周期去表示。OK， 所以这个大家回去练习看看。OK， 好，谢谢。OK。Okay, so right. So for this particular example here, we have this set of Fourier series complex Fourier series coefficients, right? For A0 plus minus 1 plus minus 2, okay, and the other within the same range of capital N values should be 0. Okay. So, right, if you you can plot this out. You can plot this out, assuming here that we're looking at the case where the period is 10. Okay. So on the left-hand side, we're representing this in terms of its real and imaginary part, right? Because the Fourier series coefficient here are general complex numbers, right? We often split this into the real and imaginary part, or we express them in terms of its magnitude and phase. Okay. So for example, when you're looking at A1, right? So A1 is 3/2 minus 1/2j, right? So you can write this as the real part plus j of the imaginary part, right? So in this case, this real part is 3/2, and the imaginary part is minus 1/2. So if you look at, A1, right, you can see here that A1 is 3/2, and the imaginary part is minus 1/2. Okay, and you see that these values, repeat themselves every period, right? So if you have a 1 at index 0, then you will also have a 1 at index capital N, 2n, and so on and so forth. Okay. Right. Now you can also represent A1 in terms of its magnitude and phase, right? So you can write it as, the magnitude A1 times e to the j theta 1, right? Or you can write them out as, A1 cosine theta 1 plus j A1 sine theta 1. Okay. So in this case, A1, okay, is, square root the square of this, which is 9/4, plus the square of this, which is 1/4. So this is square root 10/2. Okay. And what about the phase theta 1? Right. So you know that if you take the imaginary part divided by the real part, you get tangent theta 1, right, which is the imaginary part divided by the real part. Okay, so this is minus 1/3. So therefore, theta 1 is minus arctangent of 1/3. Okay, so you can see here that this magnitude A, if you express in terms of the magnitude and phase, right? Magnitude A1 is this square root 10 over 2, right? And minus arctangent 1 over 3 is some negative phase that is less than less than pi over 2, right? So it's this negative value here, and again it repeats itself every integer multiple of capital N. Okay, so this is just utilizing this example to show you how you would illustrate the Fourier series coefficients when they are in general complex numbers. Okay. Right. Now let's move on to this very typical example of periodic square waves. Okay, so we looked at this exact example in continuous time, and now we're looking at this case for discrete time. Okay, so this signal takes on the value 1 from minus n1 to n1 and 0, okay, everywhere else. But it repeats itself every integer multiple of capital N, right? So the period here is capital N. So therefore, for a signal that is periodic with period capital N, you can represent it as as its Fourier series representation using the complex exponentials with period capital N. Okay. And you can extract out the coefficient AK by taking the inner product between xn and the corresponding complex exponential. Okay, so in this case, xn is equal to 1 from minus n1 to n1. So the summation becomes a summation from minus n1 to n1 of 1 times this complex exponential. Okay. Now we can start out with the case where k is equal to 0. Right. So for the case where k is equal to 0, or any integer multiple of capital N, right, plus and minus n, 2n, and so on and so forth, right, we have the coefficient AK equal to 1 over n summation of 1s, right, because if k is equal to 0, the exponential is just 1. So we're summing over 2n1 plus 1 terms of 1 divided by n. Okay. To save space, let me write this up here. Okay. Now, for the case where k is not equal to 0 or plus minus n, plus minus 2n, and so on, okay, this ak, right, which is given up here, I can, rewrite this by a change of variable to shift the summation, okay, from minus n1 to n1 up to 0 to 2n1 plus 1. Okay, so I do this by a change of variable where we set m equal to m plus capital N1. Okay, so if we do that, then this summation, right, originally from minus n1 to n1, becomes a summation over m from 0 to 2n1 plus 1. Okay, and then inside I have this e to the minus j k e to the minus jk 2 pi over capital N. And now this N becomes M minus capital N1. Okay. Okay. Now I can then bring this N1 outside, right? Because it has nothing to do with the summation over M. So I can write this as 1 over N e to the j k 2 pi over N and 1. Okay. And then inside I have a summation from 0 to 2n1 plus 1 e to the minus j k 2 pi over capital N M. Okay. So here we have a summation over a geometric series. Okay, so by applying the formula for the summation of a geometric series, we can write this. Okay, we can write this summation as, 1 minus e to the minus j k 2 pi capital N of 2 capital N 1 plus 1, okay, divided by 1 minus e to the, so I'm sorry, I think this summation should be only up to 2n1, right? So that I have a plus 1 here, okay? And this is 1 minus j k 2 pi capital N in a denominator. Okay. So this is just applying the formula for the summation of a geometric series. Okay. Now just with a little bit of manipulation, right? So I want to bring half of this outside of the bracket. Okay. So let me bring half of this outside, which gives me e to the minus j k 2 pi capital N of capital N1 plus 1 half times e to the j k 2 pi capital N N1 plus 1 half minus the same thing. Okay. And in the denominator, I want to do something similar. I bring out half of this. So I get e to the minus j k pi 2 pi over capital N 1 half e to the j k 2 pi over capital N 1 half minus e to the minus j k 2 pi over capital N 1 half. So these terms cancel out, right? These terms cancel out. And then inside here, when we take one complex exponential minus the complex conjugate of it, we get 2j, the sign of this face, and similarly in the denominator. So 2j canceling out from both the numerator and denominator, we then get 1 over n sine of 2 pi k n1 plus 1 half over capital N divided by sine pi k over capital N. Right. So you can see that we get a formula that is a little bit like what we get in the continuous time case. Right. So here we have, the ratio of two sinusoids, right, with different values of k depending on the index of the Fourier series coefficient.
老师，
请说。
我可以问一下那个，就是最后一行那个分数，那个上面那个 sin 最后面那个符号是什么
？sin 这一个吗？
对对对。
它最后
最后面那是
这除以大 N。
好。
对，就是上面这个。对。它其实这个中括号里面就是上面这里。就是 by Euler's relation， 我可以把这写成 cosine 加 j sin 嘛，那 cosine 因为相减的话就减掉了，对，然后因为这里有一个负的，所以减负的就变成又加了一次那个 sin 的部分，所以我其实是有 2j sin 这个 face， 那下面也是我有 2j sin 下面这个 face， 那 2j 上下消掉，所以就会剩下这个样子。
了解，谢谢老师。
好 ，OK。Right, so here we have the ratio of two sinusoids, okay? Now you can sort of view this as samples of sinusoids at, integer multiples, right? If you view k, different k values as different integer multiples of this n1 plus 1 over 2 over capital N, right? And in the denominator, this is sampled at integer multiples of 1 over capital N. Okay. So as capital N increases, right? Suppose that your period increases, meaning that these periodic square waves are separated more and more apart. You're sampling these sinusoids at a denser and denser rate. Okay. So for a larger period, for a larger capital N, these square waves are more separated in time. Right. But if you look at the Fourier series coefficient, you would be, equivalently sampling these sinusoids at a faster and faster rate. Okay. So we actually have a couple of examples here. Right. For all these examples, we're setting n1 equal to 2, but with different periods. Right. This is n equal to 10, n equal to 20, n equal to 40. Okay, so you can see that as this period increases, right, you're sampling this ratio of sinusoids at a denser and denser rate. Now, if you recall, in continuous time, there was a lot of argument between mathematicians about whether or not you can use a Fourier series representation, basically a linear combination of complex exponentials, to represent a discontinuous signal like the periodic square wave. Okay? So in continuous time, we showed that, by Michelson's observation, you see that if you use a truncated Fourier series to approximate a square wave, right, you will get something like that looks more and more like a square wave, but there continues to be small ripples above and a spike at the edge by 9%, which we call the Gibbs phenomenon. Okay, and you would need the number of terms, right? You would need the summation over these Fourier series to go to infinity in order to well approximate this square wave. Okay. But in discrete time, this is not an issue, right? In discrete time, we already showed at the very beginning that, no matter what is the value of x, as long as, it is periodic with period capital N, we will be able to perfectly represent it using its Fourier series representation. Okay. Now you can sort of observe this for the square waves here. Okay. So suppose that we again take a truncated Fourier series representation like we did in the continuous time case, right? So instead of summing over, capital N consecutive values, suppose we sample, we sum over a smaller range from minus capital M to capital M, okay? So here we're assuming that the period capital N is odd, okay? It's odd. Now, if it is even, then you just sum over an even number of terms, right? Going from minus M plus 1 to capital M, okay? But this is not that critical for our discussion, okay? So suppose that, in the discrete case, we'll also look at this truncated truncated Fourier series representation. Now, if you take capital M equal to 1, right, you would get something that looks like this. Okay. Now, if you increase M to 2 terms, to 3 terms, you will see that you get something that looks more and more like a square wave. And eventually, when you increase capital M to 4, you get back exactly the square wave, exactly the square wave, okay? So here we're looking at the case where N is equal to 9 and 2N plus 1, that is equal to 5. Okay, so when M is equal to 4, right, you're summing from minus 4 up to 4, which is 9 consecutive index values, okay? So 9 consecutive terms is sufficient to represent perfectly a periodic signal with period 9, right? So you can see that, indeed, right, as we increase M from 1 to 3 to 4, we eventually are able to perfectly reconstruct the square wave. And this is done without, any convergence issues. Okay, so we do not have this overshoot given by the Gibbs phenomenon, and we do not require, infinite summation to push this, this peak to the discontinuity point. Okay. So there is no convergence issue. Okay, which we call the Gibbs phenomenon, right? Or say there is no okay, and this is true in general, right? Not only for periodic square waves, since xn is completely specified by a finite number n of parameters. Okay. So this is in contrast to the continuous time case where we need to take the summation over infinite terms, right? So for continuous time signals, you would require infinite number of parameters, right? Infinite number of these Fourier series coefficients in order to well represent your signal. Okay. So, all Right. So I didn't get to where I wanted to get to, but what we wanted to talk about next is the properties that we can derive for discrete time Fourier series, like what we did in continuous time. And, go back to the very beginning where we talked about why we want to represent signals in terms of linear combinations of these complex exponentials, okay? So the main motivation for this is that these complex exponentials are eigenfunctions of linear time-invariant systems. So if we can represent signals in terms of linear combinations of complex exponentials, then we can also easily obtain their output in terms of linear combination of the same complex exponentials. The last time we started to talk about the Fourier series representation for discrete time periodic signals. Okay, so in particular, we're interested in periodic signals that can be represented in this fashion, right? Represented as a linear combination, of the set of harmonically related complex exponential signals. Okay. Now, what's different from the continuous time case is that in discrete time, the set of harmonically related complex exponentials is finite. Okay, so in particular, if you're looking at these complex exponentials with period capital N, then there are only capital N distinct harmonically related complex exponentials. All right, so when you write this Fourier series representation, there's only the need to sum over capital N consecutive terms, okay? So this is in contrast to the continuous time case where the summation goes to infinity, right? Because each index represents a different complex exponential in the in the continuous time case. Okay. Now the question is, does there exist a Fourier series representation for all discrete time periodic signals? And the answer is yes, because because asking whether or not this expression exists for all periodic signals x of n is equivalent to asking whether or not you can find these coefficient values such that this equality holds for capital N consecutive values of x. Okay, and because what this gives you is a system of linear equations where you have capital N equations and capital N unknowns to solve. And since these linear equations are linearly independent, therefore the solution must always exist and is unique. Okay, so just by looking at this system of linear equations, we can infer that a Fourier series representation exists for all periodic, discrete time periodic signals. Okay. So then we went on to look at a few examples. All right, so we looked at the case of a pure sinusoid, and through these examples, you can see that indeed the Fourier series coefficients are periodic as well in terms of its index. Okay, so the Fourier series coefficient values start to repeat itself every integer multiple of capital N. Okay, so it's sufficient to just look at only a window of capital N values. Now, similar to the continuous time case, you can also derive some basic properties of discrete time Fourier series, and these properties will help you, make computations, these Fourier series computations, more easier for more complicated cases. Right. So using these basic operations, you will be able to compute more easily, complicated Fourier series representations. Okay, so the derivation of each one of these is, rather straightforward, similar to the continuous time case. So we're not going to go through their derivations, okay? But we can, look at a few examples. So in particular, we have in the following multiplication, the first difference, and the Parseval's relation, okay? So we're just going to quickly go through these three as an example, but for you, you should go back and try to derive each one of these yourself, just by the just by applying the Fourier series representation that we gave at the beginning. Okay, so all these derivations are rather straightforward, similar to the continuous time case. Okay. So let's go through this, faster, because this is the same, more or less the same as the discrete, continuous time case. All right. So again, we can give the shorthand notation here to represent the relation between the discrete time signal and the Fourier series coefficient. Right. So there's a double-headed arrow with Fs on the top to represent Fourier series. Okay. Now, for the multiplication property, this is saying that if you have two signals, xn and yn, with Fourier series coefficients ak and bk, respectively, and that both of these signals are periodic with period capital N, okay? Then you can show that if you take the product of xn and yn, right, this product will also be periodic with period capital N, and that the Fourier series coefficient of this, multiplication signal will be equal to the convolution of the Fourier series coefficients of xn and yn, respectively. Okay. Now notice that here, when we compute this convolution over the Fourier series coefficients, the summation is only over capital N consecutive values. Okay. So this is referred to as a periodic convolution. So for the first difference property, right, this is saying that if you have a signal xn whose Fourier series coefficient is ak and is periodic with period capital N, then the first difference equation, which is x of n minus x of n minus 1, would certainly also be periodic with the same period. And the Fourier series coefficient is equal to this given here. Okay. Now you can derive this using the linearity property, right? You can first compute the Fourier series coefficient of xn and the Fourier series coefficient of minus x of n minus 1, and then add them together to get this. Right. So you can see here that, this second term here represents a time shift in the time domain signal, right? So if you recall, right, similar to the continuous time case, a shift in time of the original signal corresponds to a phase shift in the Fourier series coefficient. Now we also get a similar Parseval's relation, which states that, on the left-hand side, which is the average power over one period, this is the average power of the signal, should be equal to the sum of the average power of each of the harmonic components. Okay, so in particular, AK absolute square is the average power of the kth harmonic component. Okay, so summing up all the average power of all harmonic components, we then get the average power of our signal over one period. Okay, So like I mentioned at the beginning, the reason for deriving all these basic properties is because knowing these basic relations help us simplify the computation of Fourier series coefficients in more complicated cases. Okay. So the key to utilizing these basic properties is being able to identify the presence of these basic properties in the problem that you're looking at. Okay, so let's look at a few examples. So these examples are more or less like the examples we looked at in the continuous time case as well. So here we're looking at a signal xn that looks something like this. Okay, so you can see that this signal repeats itself every 5 samples. Okay, so you can see that this is 22211, and then again you have here 22211. Right, so it's repeats itself every 5 samples. So the fundamental period is equal to 5. Okay. Now, by observation, you can see that this signal xn can actually be split into 2 signals. So first of all, we can think of this as having this signal 1, 1, 1, 0, 0, 1, 1, 1, okay, 0, 0, 1, 1, 1, 0, 0, so on and so forth. Okay, plus a signal that is constant 1 over all time indices. Okay. So plus a signal that is equal to 1 over all time. Okay? Right, so if you add these 2 signals, you will see that, let's say for n between -1, 0, and 1, 1 plus 1 is 2, right? And for n equal to 2 and 3, right, 0 plus 1 is 1. Okay, so let's call this signal x1n and this signal x2n. Okay, so xn is equal to x1n plus x2n. Right. Now suppose that xn has Fourier coefficient ak. Okay, x1n has Fourier coefficient bk, and x2n has Fourier series coefficient ck. Okay. So first of all, by linearity, we know that since xn is equal to x1 plus x2, ak must also be equal to bk plus ck. Okay. Now, to first obtain the value of bk, right, if you look at this signal here, you will see that this is a periodic square wave, similar to what we looked at in example 3.12. So if you look back to example 3.12, right, in example 3.12, we looked at a general periodic square wave where the square ranges from -n1 to n1, and it repeats with period capital N. Okay. Now in our case, this is equivalent to having a periodic square wave with n1 equal to 1 and with period capital N equal to 5. Okay. So from example 3.12, for n1 equal to 1 and n equal to 5, right? We can directly take the result that we obtained there to get bk equal to 1/5 sine 3 pi k over 5 divided by sine pi k over 5. Okay. For k not equal to 0, plus minus 5, plus minus 10, so on and so forth. Okay. And simply 3/5 for k that is 0, plus minus 5, plus minus 10, and so on. Okay, so this is obtained by just taking the result that we derived from example 3.12. Okay. Now, for x2n, x2n is simply equal to a constant. Okay, so only the Fourier series coefficient corresponding to the constant a DC component of the harmonically related complex exponentials would have a non-zero value. Okay. So for x2n, we have only a constant, and in that case, the coefficient, this corresponds to a coefficient C0, that is just the average of the samples over one period. Okay, and this is equal to 1. Okay, so in fact, this is for all k, that is 0, plus minus 5, plus minus 10, and so on. Okay. Now, if k is not these values, then it must correspond to a sinusoid that would not have any, factor here because the signal is just a constant. Okay, so this ck would be 0 for all k not equal to 0, plus minus 5, plus minus 10, and so on. Okay, so if you take ck and bk, plug it back into this equation above, you can then find the Fourier series coefficient for ak. Take ck and bk, plug it back into this equation above, you can then find the Fourier series coefficient for ak. Okay, so hence you get ak that is equal to, right, if k is 0, plus minus 5, plus minus 10, then you have 1 plus 3/5, which is 8/5, right, for k not equal to, k equal to 0, plus minus 5, plus minus 10, and so on. Okay. Now, if you have k not equal to 0 plus minus 5 and so on, then you have ck0 plus bk, which is this. So this is essentially bk, which is 1 over 5 sine 3 pi k over 5 over sine pi k over 5. Okay, where k not equal to 0, plus minus 5, plus minus 10, so on. So do we have any questions here?
老师，那个 BK 那个 sin 的那个方程式是怎么看出来的啊？
这个就是从 3.12 的结果得来的。
直接用它的结果是吗？
对。
好的，谢谢。
所以在这里我们就是套用 n1 等于1，然后大 N 等于5的情况到下面这个式子来。对，所以大 N1 如果等于1的话，这里就是3/2嘛。那2 cancel out， 这里就是3 pi k over 5。大 N 是5。OK， 那分母就是 sin pi k over 5这样子。可以吗？
老师，那个 for n 等于，那是 n1 等于1吗？
对 ，n1， 觉得有点歪，是吗 ？n1，
教授，
是，
想要请问一下 CK 是怎么求的
？CK 就是用我们的 Fourier series 的这个式子求的。就是这个式子求的。OK， 那当你在看k 等于0这一项的时候，就是 c0的话 ，k 等于0这一项，这个 exponential 就只是一个 constant 1嘛。所以 c0这一项其实就是去平均我的讯号 over one period。可以吗？
那就是为什么它是就是在正负10的时候才会有值这样？
对，那就是说，当然你也可以去把它一个一个求出来 ，OK。OK， 就是说你当然也是可以把它一个一个求出来 ，OK， 但是因为你这个 c0项就已经等于1了 ，OK， 所以你这个1就已经是 reconstruct 原本的 x2n 这个讯号了，它就是全部都是1 ，OK， 所以其他的这个 ck 其实一定都是0。那如果你要的话，你也是可以把它确切的算出来哦。就比如说的 ck 如果按照刚才的公式的话，就是这个 summation xn e to the minus j k 2 pi over capital N and over one period, which you can take as summation from 0 to 4. Right. 那因为 xn 都是1嘛，这里的 这里是 x2n。OK， 所以 x2n 都是1，所以其实这就是 summation of the complex exponential. OK， 那当你 sum over one period of a complex exponential of 这个 periodic 的 complex exponential， 它正的就像是一个 sinusoid 一样，它的正的地方就跟负的地方 cancel 掉， 所以你 sum over one period of a sinusoid 就会等于0。
哦，了解，谢谢教授，谢谢教授。
所以我想更精确的话，这里大 N 是5，可以直接带5进去。对不起，这里应该是 sum 到4而已。OK， 就是说你们可以就是说确切就是每一个 CK 都把它算出来，但事实上在这里是没有必要的，因为你光算出 C0 C0 等于1就已经是完整的 reconstruct 这个x2n 这个讯号了。OK， 所以其他的 coefficient 一定都是0。
教授，
是。
我想请问，为什么那个 n1 是1
？n1 是1，就是你手上有那个 3.12 那个 example 吗？
有。
所以 3.12 那个 example， 它 n1 就是设定是从 minus n1 到 n1 这样子。那我们在这里 n1 就是1。
OK。谢谢教授。
好。Okay, so let's maybe move on to the next.
老师。
对，好 ，OK。
抱歉，那个可以讲一下蓝色部分吗？蓝色部分可以再讲一次吗？
就说确切哪一个地方？
就是为什么这样会是0？
你说最后这个为什么是0吗？
对。
因为当然你可以就把它展开，你可以把它展开就自己算一次，你就会看到它是等于0了。但是就说如果你从这个图解来，就说从intuitive 的图解来看的话，因为这个 complex exponential 就是一个 sinusoid， 它的 real part 跟 imaginary part 都是一个 sinusoid。那你这个是 sum over one period of a sinusoid， 所以正的地方就会跟负的地方加起来 cancel 掉。对，但是你就是确切把它展开算一次，也是可以的。对。
好，谢谢老师。
好。Okay. All right. So in this example, we gave several conditions, and you're asked to find what this signal x of n is, right? So we had a similar example in the continuous time case. Right, so first of all, here we have the first condition says that xn is periodic with period capital N. Okay, so we know by the first condition that the signal has period capital N equal to 6. Now, by this second condition, we know that the summation of xn from 0 to 5, which is a summation over one period, is equal to 2, right? So, maybe from this previous example, you already see that, summation over one period helps you compute the coefficient for k equal to 0, right? So by 2, right, we can compute the coefficient for k equal to 0, which is 1 over the period times the summation over one period, okay? And since this summation is 2, this is 1 over 3. Okay. Now, again, by 3, we know that the summation of n equal to 2, from 2 up to 7, of minus 1 to the power n x of n is equal to 1. Okay. Now notice that this is also a summation over one period, even though the starting point and the ending point is different from the above, but it's taking a summation over capital N consecutive values. Okay. Now, furthermore, you can observe that -1 to the power n can also be represented in terms of a complex exponential. Right. So in particular, by 3, notice that since -1n, you can write as e to the minus j pi n. Okay. E to the minus j pi is -1. Okay. So e to the minus j pi n is -1 to the power n. And then you can further write this as e to the minus j 2 pi over 6, where 6 is the period, times 3n. Okay. So if you look at this, you can see that this is actually the complex exponential corresponding to the coefficient with index k. Okay. So this means that, if you represent -1 to the power n as this, what this summation gives you is something that helps you compute the coefficient A3. Okay. So A3, which is 1 over 6 summation over one period, let's take 2 to 7 xn e to the minus j 2 pi over 6 3n. Okay. Now this is equal to 1 over 6 summation n from 2 to 7 minus 1 to the power n xn. Okay. Now we know by 3 that this summation here is 1, so this coefficient is just 1 over 6. Okay. So now we have the coefficient values for A0 and A3, right? Now the fourth condition tells us that xn has the minimum power per period among the set of signals satisfying the previous 3 conditions. Okay. So we know that for a signal that is periodic with period n equal to 6, we can write it in terms of its Fourier series representation, where xn should be equal to summation a k e to the j k 2 pi over 6 times n from, let's say, 0 up to 5. Okay? Now, A0 we know is 1 over 3. A3 we know is 1 over 6. So, any signal that satisfies the first 3 conditions should be able to be be represented in this form with A0 and A3 given by 1 over 3 and 1 over 6 respectively. So the only values that are not specified are A1, A2, A4, and A5. Okay. But condition 4 tells us that xn has the minimum power per period among all signals that satisfy these 3 conditions. Now, by Parseval's theorem, right, when you see minimum power per period, right, you intuitively think of Parseval's theorem, okay, Parseval's relation, right? Because Parseval's relation tells us that Parseval's relation tells us that the average power of the signal over one period, right, which is 1 over 6. Okay, let's denote this by P. Right, the average power over one period is 1 over 6 n summed over one period xn squared. Right, should be equal to the summation of AK squared, K from 0 to 5. Okay. So if you're saying that Xn is the signal with the minimum power satisfying these conditions here, then this by Parseval's theorem, we know that A1, A2, A4, and A5 should all be 0, right? Otherwise, you would be increasing the average power. Okay. So by 4, we know that AK should be equal to 0 for K equal to 1, 2, 4, 5. Okay. So then by plugging all these values back into this Fourier series representation, we find that Xn is 1/3. Okay, or let me say A0 plus A3 e to the j 2 pi over 6 3n. Okay, which is 1/3 plus 1/6 to the up 1/6 minus 1 to the power n. Okay. Okay. So you can also plot this out if you like. So here you have Xn. So when n is even, right? When n is even, minus 1 to the power n is 1. So we have 1/3 plus 1/6, which is 1/2. Okay. So let's say this is 1/2. You get 1/2 here, 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 and so on. Now for n that is odd, right, you have 1/3 minus 1/6, which gives you 1/6. So you have points here, here, here. And so on. Okay.
老师，
请说。
问一下第4点嘛，就是再解释是第4点。为什么？
OK， 所以Parseval's theorem, Parseval's relation 告诉我们说，这个讯号的 average power 就会等于它的这个 Fourier series coefficient 的这个平方，就是绝对值平方的和。OK。
对。
那我前面3个 condition 让我知道的是说，这个 A0 会是1/3，然后 A3 会是1/6，所以 A0 跟 A3 是不能动的。Okay. 那如果说我希望这个讯号是有 minimum 是符合这条件的这个拥有 minimum power 的这个讯号的话，那么我就必须要让其他的 coefficient 等于0。
所以第4点的意思是说，就是在所有符合前面3点的情况下，还有最少 power 的那一个。
对对。
好。
OK， 谢谢。
谢谢老师。
So if not, let's move on to the last example. Okay. So in this last example, we're going to utilize this property here from the table. Okay. So this is sort of a dual property of the multiplication property, right? So previously we showed that if you have multiplication in the time domain signal, then the Fourier series coefficient would be equal to a periodic convolution. Okay. Now this is true the other way around. If you have a signal Wn that is equal to a convolution between two signals, x and y, then the Fourier series coefficient will be equal to the product of their respective Fourier series coefficient multiplied by the period capital N. Okay, so utilizing this property, we're asked to answer the following question, right? So suppose that Wn is periodic with fundamental period capital N equal to 7, and that the Fourier series coefficient takes on this form here. By observation, you can view this CK as 1/7 times this sine over sine squared. Okay. So by observation, we can view CK as actually, let's say 7 times dk squared. Okay. Where dk is 1/7 sine 3 pi k over 7 sine pi k over 7. Okay. Now, why do we want to write it like this? Okay. So I hope that a Fourier series coefficient like this looks familiar to you, right? Because we just used it in a few previous examples. Okay. So in particular, this is actually the Fourier series coefficient of a periodic square wave, okay, with n1 equal to 1 and period capital N equal to 7. Okay. So this actually is the Fourier series coefficient of a signal, okay, of a periodic signal, okay, that is a periodic square wave with n1 equal to 1 and period equal to 7. Okay, so you have a 1 here, here, and here, right? From -1 to 1, 0 here, and repeats itself again here, 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 and so on. Okay. So if you are able to observe this fact, right, if you are able to observe that CK is equal to 7 times dk squared, where dk is actually the Fourier series coefficient of this periodic square wave, then by the property above, you know that the signal Wn that you're looking for can be obtained by taking the periodic convolution of x of the signal x and itself. Okay. So hence, this Wn that you're looking for should be equal to the convolution between x and itself for R summing over one period. Okay. Now, in particular, we can limit this summation from -3 to 3. All right, we're taking this summation over 7 consecutive indices, okay, of xr, x of n minus r. Okay, Now, instead of doing this directly, right, since we're only limiting our summation over only one period of the signal xr, okay, this is equivalent to looking at the summation over some effective signal xr hat, where xr hat is equal to xr for r within this range, but 0 everywhere else. Okay, so where this x hat n is equal to xn for n between -3 and 3 and 0 otherwise. Okay, so if we replace xr with this x hat of r, we can then take this summation from -infinity to infinity xn minus r. Okay. So, right, so here we have this example where xr looks something like this, right? So here n1 is equal to 1, so you have ones from -1 to 1, right? 0 for 2, 3, 4, 5, and then 1, 1, 1 again, right? So this thing repeats itself, every capital N equal to 7, right? So 1, 2, 3, 4, 5, 6, 7. Okay. Now I want to take the convolution between xr, which is this, and itself. Right. So x of n minus r is xr flipped around and shifted to time n. Okay. So x of n minus r is xr flipped about the origin, but then moving the midpoint to n. Okay. Now, instead of looking at xr directly, we look at the effective signal x hat of r, right? That is equal to 0 outside of the range of summation. Okay. So the reason for doing that is because, then we have x hat of r that looks cleaner, right? We don't have to worry about what happens in other areas of the time index. Okay, and then we take x hat r, convolve it with x of n minus r, right? That is flipped around and shifting the center to time n. Okay, and multiplying these two signals pointwise and summing it up gives you the signal Wn that you want. Okay. So in particular, so suppose you want to compute W0, right? So W0 is summation, x hat r, x of n minus r, r from -infinity to infinity. Okay, so here n is 0, right? So this is 0 minus r. Okay, so this x of minus r is simply x of r flipped around, right? So when you have x of r flipped around and multiplied with this, you have 1, 1, 1 here and 0 everywhere else. Okay, so this is just summation r from -1 to 1 of 1, which is 3. Okay. So similarly, when you compute x of -1, w of -1 or w of 1, right? You take the convolution, you multiply this x hat of r with x of n minus r, where n is equal to 1 or -1 in this case. So if you move the center point to 1, then you will have 2 points that overlap. So when you multiply, you get 1, 1 at times 0 and 1, and 0 everywhere else. So when you sum that up, W1 is equal to 2. Okay. So continuing this fashion, you can find W of minus 2 and 2, which is equal to 1, and then W of minus 3, W3, that is equal to 0. Okay, so therefore you have specified what the signal looks like over one period. Okay, and this is the plot of your final outcome. Okay, so do we have any questions here?
老师可以再讲一次为什么那个-1等于1，然后-2等于2吗
？OK， 这个其实就是，就是说这个我没有去讲 detail， 因为它其实就是算一个 convolution 而已。那这个我想大家回去都可以自己算 ，OK？ 那其实，你想想看，你要算 convolution， 你就是，你这是 x hat of r，right？ 然后你这是 x of r， 你要把它 flip around， 然后 shift 到比如说如果 n 等于1的话，就是往右边 shift 一格。那往右边 shift 一格，就是说你 point y 相乘的话，这个1就会跟这个1相乘，这个1跟这个1相乘，那其他的地方相乘都是0。所以说你把它加起来的话，就会等于2。OK， 那这个 detail 我相信大家回去应该是有办法自己算，所以我就不把它那个写出来这样子，好不好？我们这个回去试试看。
好，谢谢。
好，谢谢。
那个教授，那我想要问一下，那个就是上一页有那个提出来的1/7，那新的系数要乘回去那个1/7吗？不然7倍啊，7倍 ，ck 等于7的 dk 平方这里。
因为我在 dk 里面有一个1/7，所以 dk 平方就有2个1/7嘛，那跟乘7以后就剩下一个1/7的。
所以后面 wn 算出来后要是乘以7嘛，就是。
哦，对，要，对，你说对了，应该要。哎，没有，不用，对不起，对，因为这个，就是说，因为我现在这个7就是这个 capital N， 对，所以我如果直接对照这个跟这个的话，那么它的 time domain 就是原本的这个 x 跟他自己的这个 convolution。
好，应该大概懂。
OK， 所以其实就是套用这个公式啊，对。那这个公式其实就是就是鼓励大家自己回去推导一遍。事实上前面的那些那整个 table 里面的公式，我都鼓励大家自己推导一遍，我觉得这个会比较有印象。OK。虽然说这个推导应该都是蛮 straightforward， 大家可能觉得就是很反复，但是就是说推导一次就会比较知道它是怎么来的这样子。OK， 还有没有其他的问题？OK。All right, so if not, let's move on. Right. So up to this point, we have talked about, whether or not you can represent periodic signals either in continuous or discrete time in terms of its Fourier series representation. So Fourier series representation is basically a linear combination of harmonically related complex exponentials. Now, the reason for looking at this is because, if you can write signals as, a linear combination of complex exponentials, then it's, the the input-output relation of a linear time invariant system becomes you get a easy and intuitive way of looking at the input-output relation of a linear time invariant system. Okay, so in particular, we showed previously that this so the reason for this is because this complex exponential is a eigenfunction of linear time invariant systems. This means that if you input a complex exponential to a linear time invariant system, the output will also be the same complex exponential, except for this gain, which can be evaluated by this formula here. Okay, so if you input this complex exponential, you get the same complex exponential, but with a different gain. And this gain can be evaluated from the impulse response. So this is true also in the discrete case, where if you input x of n equal to z to the power n, then you get the same z to the power n at output scaled by this gain h of z, which you can also compute by the impulse response. Okay, so this holds in general for any s and any z. So in general, if you're looking at general complex values of s and z, then we call this h of s and h of z system functions. Okay. But if you're looking at particular cases where s is equal to j omega or z equal to e to the j omega, then these complex exponentials correspond to pure frequency components, and therefore the system functions, right, this hs and hz, are then called frequency responses. Okay, and we're going to be looking at these cases most often, right? Okay. So consequently, in continuous time, if you say that your signal x of t can be represented in terms of this linear combination of these complex exponentials with pure frequency components, right? Then the output y of t would be a linear combination of the same harmonically related complex exponentials with the gain altered by this h of j k omega naught, where k omega naught is the corresponding frequency of this complex exponential. Okay? And this value you can readily compute using this formula up here. Right. So you can see here that, by passing a signal through a linear time invariant system, the signal is modified. This linear time invariant system modifies each frequency component individually, right? Using this gain here. Okay. So an LTI system modifies the gain of each frequency component individually. Okay. So this helps you gain further insight about what happens when a signal goes through a linear time invariant system. Right? You can sort of see, which frequency components this system amplifies and which frequency component this system maybe suppresses. Okay. So let's look at this example here, which is the same as example 3.2. Okay, so here we have x of t, right, equal to this summation from -3 to 3 ake e to the jk 2 pi t. Okay, with coefficients given down here. So suppose that this signal is passed through a linear time invariant system with impulse response equal to this. Okay. Now suppose you want to know, right? You want to obtain the output signal. Okay, you want to obtain the output signal. Right. So what we can do is that we can first compute the frequency response to this system. Okay. So for this system, we can compute the frequency response, h of j omega, as the integral of h of tau e to the minus j omega tau d tau. So if I plug this inside, I then have an integral from 0 to infinity e to the minus tau e to the minus j omega tau d tau. Okay, so if you work this out, you get 1 over minus 1 plus j omega, right? Because you get minus 1 plus j omega tau in the exponent here, e to the minus 1 plus j omega tau for tau with the upper and lower limits 0 and infinity. So if you plug this in, then you get 1 over 1 plus j omega. Okay. So we know that if the input is this linear combination of complex exponentials, then the output y of t must be a linear combination of the same complex exponentials okay, times the gain h of j two pi k. Okay, so if you take this, plug it inside, then what you get is summation k from -3 to 3 ak 1 plus j omega e to the j, oh, I'm sorry, 1 plus j 2 pi k e to the j k 2 pi t. Okay, so let's denote this. So this is the coefficient, the Fourier series coefficient for the output signal y of t. Okay, so let's denote this as bk. Okay, so if you plug in, ak given above, right, you will find that b0, okay, b0, which is a0 over, okay, over 1 plus 0, okay, is 1, right? b1 is equal to 1 over 4 times 1 over 1 plus j 2 pi. Okay. b minus 1 is 1 over 4, 1 over 1 minus j 2 pi. Okay. and so on and so forth. Right? So B2 is 1/2. 1/2 is A2, right? Times 1/1 plus J 4 pi. B minus 2 is 1/2. 1/1 minus J 4 pi. B3 is 1/3. 1/1 plus J 6 pi. And B minus 3 is 1/3. 1/1 minus J 6 pi. Okay? So these Fourier series coefficients for y of t are obtained by simply plugging, different values of k into this formula here with ak given in the problem. Okay. Now, if you look at this, you will see that B1 is a complex conjugate of B minus 1. B2 is complex conjugate of B minus 2, and same for B3 and B minus 3. Okay. So we know that if this is the case, right, so notice that BK is equal to B minus K complex conjugate for all K. Right. So this means that it is conjugate symmetric. Okay. And when this is the case, we know that the signal must be real. Okay. So suppose we write BK, right? So if BK is complex, right, there are two ways to represent it, right? We can either represent it in terms of its magnitude and phase, okay? Or we can represent it in terms of its real part and imaginary part. Okay. Now, since BK is equal to, B minus K complex conjugate, this YT here can be represented in a more compact form, equal to 1 plus 2 summation K from 1 to 3, the real part of dk e to the j 2 pi kt plus theta k. Okay. And this would be equal to 1 plus 2 times summation dk cosine 2 pi kt plus theta k. Or if we represent bk as ek plus jfk, then we can write this as 1 plus 2 times summation k from 1 to 3 ek cosine 2 pi kt minus fk sine 2 pi kt. So these are just alternative expressions for your output signal y when your input is real and therefore the output is real. Okay.